Good morning, everyone. Welcome to day 2 of HAID. And our next session is on issues of perception. And it's going to be chaired by Professor Hong Tan.
Good morning. So our first presenter is Angela, and his talk is on effects of subthreshold vibration and the perception of electrovibration.
Thank you. Good morning, one and all. So my name is Jagan. I'm a research scholar at IIT Madras, India. So my work is about how mechanical vibrotactile stimulus affect the perception of electrovibration. So these are my co-authors, Mr. Rahul Kumar Ray and Dr. Manivan Munyandi. So he is my supervisor. So I'm part of haptics lab at IIT Madras. Okay, so these are the outline of the of today's presentation. So I'll be talking a bit about the electrovibration principle, the previous work that is being done in the same exact way, and then the theory related to the subthreshold vibrotactile stimulus, and then the experimental study that we conducted and the results that we got, and a bit about the discussion of the results, and then the future works. And later I'll be willing to take questions from this presentation. Okay, so. Electrovibration is basically comes under surface haptic techniques, where you get frictional feedback from a smooth surface. So the idea is that you employ electrostatic force to actuate the mechanoreceptors that are present in our fingers. Okay. So the idea of how this works is that you supply a high voltage signal to a conductive layer, which is coated with an insulating layer, and then on top of that you keep your finger, and when you place your finger there is a electric field that is induced, which in turn causes an electrostatic force of attraction between the conductor and the finger. Okay, so this force, if you see, if you give a DC signal, the force when you move your finger will not be felt, or you will not feel any frictional sensation, because it is an equipotential surface. So in order to have a sensation, we have to give an AC signal, so that with the time varying signal, the electrostatic force also changes, and then that helps you to perceive the electrovibration. Okay, so this theory is basically modeled as a parallel plate capacitor model, where the conductive layer is one plate of the capacitor, and then the finger becomes the other plate of the capacitor. So here is a bit of equation of how the electrostatic force relates to the applied voltage to the electrovibration tactile display. That you have electrostatic force directly related to the square of the applied voltage, and A is the area of contact, and Ts is the thickness of the stratum corneum, and Tp is the thickness of the insulating layer, where epsilon s is the dielectric constant of the stratum corneum, and epsilon b is the dielectric constant of the insulating layer. So when we plug in few values, we get that if in order to feel a frictional force of around 1 to 1.4 newtons, we have to give a really high voltage for any person to feel a sensation, because the kinetic friction coefficient also comes into picture when you feel the friction from the display. So Fn is the normal force, Fe is the electrostatic force, and mu is the kinetic friction coefficient. Okay. Okay. So this is with regards to how electrovibration display works, but we wanted to see whether other tactile multimodal stimuli has an effect with electrovibration. We wanted to see how vibrotactile stimulus interacts with electrovibration when users are trying to touch the surface. Okay, so previously there was one work done by Ryu et al. So they have studied the influence of vibrotactile stimulus and electrovibration at suprathreshold, that is way beyond the threshold of what humans recognize. And then they concluded that when you give two stimuli together, they felt like one stimuli is trying to mask other stimuli, in the sense that, let's say you give vibrotactile stimulus with electrovibration. Without any vibrotactile stimulus, electrovibration can be felt at around 50 volts, peak to peak. And when you give a vibrotactile stimulus, the threshold suddenly increases to 75 volts. This is sort of decremental in the way when you are trying to create a display, because you are now increasing the threshold, which also possesses other safety concerns, and then people may get an unpleasant sensation when they interact with it. And later, Jamal et al. Investigated this remote masking of electrovibration. So they placed a LRA on the finger, and they also created an electrovibration display, and figured out that there is also, irrespective of the location of the LRA, there is always an increase in the threshold of electrovibration. And so what we wanted to do is, we wanted to see whether it is possible to, try to reduce this masking effect and thereby reduce the threshold of electrovibration. So what we did is, in our lab, one of my co-authors worked on an electrotactile display, which is similar to an electrovibration display, but the thing is that it doesn't have any insulating layer. So we found out that by giving thermal stimulation and then as well as vibrotactile stimulus, you get a reduction of 13% to 17% for thermal stimulation, and with vibrotactile you get 3 to 5%. But since there is no insulating medium to the display, people have complained that they have feeling, the unpleasant sensation of shock, and any change in the skin impedance will in turn result in this, accelerate this process of feeling unpleasant sensation. So we wanted to move out of this electrotactile display, and then we wanted to go into electrovibration, where the mechanoreceptors are actuated. That when electrotactile, it's the mechanoreceptors plus the free nerve endings, and the display is directly coupled to the finger. So, and in the previous study, we also found out that the reduction in threshold for vibrotactile stimulus is only 3 to 5%, which is lower than the just noticeable difference for electrotactile stimulus, which is 16%. And when you give background thermal stimulation, the display itself has a very low refresh rate, because LTS that was used takes time to achieve the desired temperature. So for our motivation, we wanted to investigate whether the same vibrotactile stimulus has an effect on electrovibration. And then we want to see, if so, how much is the percentage of reduction, and also whether tactile masking is happening. So the way this study was conducted is that you have a normal conductor. On top of that, you have an insulating medium. And then we have 4 LRAs that are placed at the corner of the display. And then we ask the subject to, touch and interact with the display. And also the threshold that was given to the vibrotactile was much, much lower than the previous studies. So we wanted to see whether this subthreshold vibrotactile stimulus has any effect on electrovibration. So the subthreshold vibrotactile stimuli were given at 90% and 80% of the actual value. And then we wanted to further investigate whether what type of sensation the subjects are feeling to be dominant. And we wanted to also explore whether tactile masking is happening in this process. So this is the setup that we used for our study. So basically, we have a high voltage power supply, which is powered through a DC source, then which is given to a driver amplifier, and a function generator is connected to the driver amplifier. So this driver amplifier takes a low voltage signal from the function generator and then feeds it to the electrovibration display. For the LRAs, we used another function generator and a LRA driver amplifier, which is basically a current amplifier, to drive all the 4 LRAs. This setup was then attached with a touch bar to detect the finger motion, and also the entire setup was placed on a XYZ table, so that the height of the setup can be adjusted and the position can be adjusted based upon the subject's height and other parameters. So in order to calculate the vibrotactile stimulus value, we used optical non-contact displacement transducers that gives a profile of the mechanical vibration, and we also used it to make sure that the LRAs are in sync. And we conducted the study with a square wave because in earlier in the literature it is found out that compared to a pure sinusoidal wave, square waves have a better higher perception level. So we used square wave to actuate both the LRAs and the electrovibration display. The electrovibration frequencies were chosen from 20 to 320 hertz, such that it covers the entire detection threshold of the human finger. And then the vibrotactile stimuli was maintained at 235 hertz because it has a resonant at that frequency, and the Pacinian corpuscle that is present in our finger are resonant at 235 hertz. So we had 4 stages for the experiment. We did a psychophysical study with 15 subjects, 7 male subjects and 8 female subjects, and all from our university. So the first stage of the experiment involved measuring the vibrotactile stimuli. So in order to measure the threshold, we used a staircase method, which is a very standard method for finding the absolute threshold of a subject. We used that method to find out the absolute vibrotactile stimuli threshold, and then for the second stage, we employed a similar method to measure the threshold of electrovibration. And for the third stage, we conducted the same experiment, but this time we gave 90% of the threshold, that vibrotactile threshold, which was measured in stage 1. And then in the final stage, we gave 80% vibrotactile stimuli, which was measured from the first stage. So then we calculated what is the threshold of electrovibration for third and the fourth stage. And we also wanted to see what sensation that the subject is feeling based upon a Likert scale rating that the subject gives. So this is the Likert scale value. So we had given to test stimuli to the subjects, and we asked them like test subjects so that they get acquainted to the vibrotactile stimuli as well as the electrovibration stimuli. And if they feel only the vibrotactile stimuli, they rate 1. And if they feel that vibrotactile is more than electrovibration, then they rate 2. And then if they feel that both are equal, then they give a rating of 3. And if vibrotactile is less than electrovibration, it is given 4. And then if only electrovibration is felt, then it is given a 5. So vibrotactile stimuli are usually felt when you keep your finger stationary, and it is like it happens in normal direction. But electrovibration sensation you'll only feel when you move your finger. So this was a difference that we told to the subjects, and then they rated the sensation based upon this. So these are the results from the study. We found out that with this current method, we have an average of 28.52% reduction in the threshold, with the maximum reduction happening at 235 Hz for 90% SPS, with a maximum threshold reduction of 30%, and the minimum percentage reduction was happening for 80% SPS at 80 Hz. It was around 10%. But for an average, if you calculate the average for 90% SPS and 80% SPS, it is found out that electrovibration threshold reduced by 28.5% and 16.9%. The average vibrotactile stimuli threshold was measured to be 0.68 micrometer, and out of the 15 subjects, the maximum that was measured is 0.196 micrometer, and then the minimum was 0.428 micrometer. And this first figure shows us the the profile of the electrovibration threshold at no SPS, which is indicated by the blue line, at 90% SPS, which is indicated by the orange line, and at 80% SPS, which is indicated by the gray line. And if you look, we see that at 90% SPS, the percentage reduction is much higher than the 80% SPS. And these values are normalized to the 20 Hertz signal, and this is an average of all the 15 subjects. And the next figure shows the Likert scale value, and we can see that people have a higher preference for. People have reported that they have felt electrovibration to be stronger when we give 80% SPS, and they feel that electrovibration is weaker for 90% SPS. And this makes sense because at 90% SPS you get to have more electrovibration sensation, vibrotactile sensation compared to 80% SPS. So we also did a statistical two-way ANOVA analysis to see whether to remove to verify null hypothesis. And we found out that the F value for variation with threshold variation with frequency is much higher than the F critical, and the P value is also less than 0.05. And similarly, variation within the subthreshold vibrotactile stimuli and electrovibration threshold of electrovibration, we found out that the F value and the P values are high and low. So this indicates that we can reject null hypothesis, and then there is statistical difference between the values that we can collect. So the reduction of threshold also tells us that when you give subthreshold vibrotactile stimuli, tactile masking doesn't happen in the case of electrovibration, and then subjects have a higher purpose. They perceive electrovibration better for 80% SPS than compared to 90% SPS. So the future work for this study is that we would like to explore for other frequencies of vibrotactile stimulus. The reason why we chose LRAs were because of their compactness, and then also we were trying to make a much smaller device, and so we wanted to go with LRAs than voice coils. So for the future study, we would like to conduct it with multiple vibrotactile frequencies. And then we would also like to introduce other type of tactile stimuli, including ultrasound based stimuli, and also electrocutaneous stimuli. And we would are also exploring a texture rendering algorithm which take advantage of SVS and electrovibration. Because if you want a subject to just feel electrovibration sensation, you can just give SVS at 90% and 80%. And if you want them to feel a combination of these two stimuli, then you can give the SVS at 90%. So it makes sense to have a texture rendering algorithm which employs these things and also reduces the threshold. So these are the references that I have used for my study presentation, and I'm willing to take questions.
Thank you.
Yeah.
Time for questions. Please.
Thank you. That's very interesting. So the electrotactile will also depend on the distance between the finger.
Yeah.
But if you add a vibrotactile on top of it, could that affect that distance by making the finger or it's too small?
It should, I believe, but we haven't explored. And there is one paper which talks about the air gap thickness between the finger and the electrotactile displays. They have concluded at higher voltage and higher frequencies, the air gap distance reduces, so the persons better perceive the sensation. I believe that vibrotactile stimuli, when you introduce, will affect this air gap, in turn affecting the height between the finger and the display. Yes.
Yes, I had a similar question. I thought given your equations, you can actually calculate. Yeah, but it'd be interesting to see because you know exactly how much displacement you display.
Yes.
Any other questions? So I also had a question. What exactly did the participant do?
Okay, sorry. So the participants were first asked to wash clean their hands, and then they were asked to move their finger from the extreme left end to the right end, and then in a monitor we displayed a small object which we basically had two objects. One object which has a standard exploration speed, and another object which moves based upon your speed on your finger speed. Okay, so your task is to just move your finger and then follow the object.
Okay.
Yes, and at the same time you are also supposed to tell us at what threshold you are feeling the sensation. In the sense, as you move your finger, there are a few intervals. So there are actually two intervals. And at the second interval, we start giving the electrovibration stimuli. Okay, and then we make sure that the threshold, the staircase method they follow is within that time interval of such that you don't have to come back again. So the subjects were asked to rate the electrovibration, answer the threshold at which they are feeling the electrovibration, and at the same time they were also asked to rate of what type of stimuli they are perceiving when you give two stimuli together.
So you have a left region, right region, and you ask them where the electrovibration.
Yeah.
And then you randomize that.
Yes. So they had to, sometimes they had to do multiple times because you only feel electrovibration when you move your finger. So we keep on increasing the voltage, and then once they say that they feel a sensation, then we reduce the voltage. Then after that they say they don't feel it, and then we increase it, and then we do it for three, 4 trials, and then calculate the average.
So it's adaptive syndrome.
Yeah.
Thank you. If there are no other questions, let's thank the speaker again. Our next speaker is Dr. Lynette Jones from MIT. She's going to talk about incorporating thermal feedback in cutaneous displays.
Okay, good morning. Thank you. So I'm going to give an overview of some of the work that we've been doing in my lab on thermal displays, and more recently I'm incorporating those with tactile feedback in what we call multisensory cutaneous displays. And for those of you less familiar with thermal sensing, we know about the temperature of things on the basis of 2 classes of receptor that we have in the skin, cold and warm receptors. We have more cold than warm, and cold receptors basically respond to decreases in skin temperature, warm receptors to increases. And so we don't have any absolute temperature sensation. Everything is relative to the baseline skin temperature. The cold sensors are located more superficially, close to the skin surface than warm sensors, and they're free nerve endings, and not like the specialized structures that you see for cutaneous mechanoreceptors. And they're activated over a temperature range of 15 to 45 degrees C. Once you go outside that range, you get into noxious cold or noxious heat, and for those sensations, the fact that the skin is being damaged is the most overwhelming perceptual event. That is, you often, if you've had frostbite or anything like that, it feels as if the skin is burning. So basically the message being sent to the central nervous system in the brain is to remove the body part from the source of tissue damage. There's been a lot of work on the underlying mechanisms responsible for sensing temperature, and these are TRIP channels, transient receptor potential channels, that are activated by both distinct physiological temperatures and natural compounds. And for those of you who were at the workshop yesterday, where his first name Lopez gave the presentation on smart haptic assistive devices of the future, he talked about using some of these chemicals that we see here, such as horseradish, capsaicin, and peppers, and so on, to elicit thermal changes in a display that would be wearable. So he called it chemical haptic displays. So this response of these channels to a cold temperature, for instance, is the same as it would have to methanol or mint. The response of these channels to hot temperatures is similar to what we see in chili peppers, the capsaicin and chili peppers. And in fact, this work on the fundamental mechanisms of thermal sensing was the recipient of the Nobel Prize in Physiology and Medicine last year. So when we come in contact with something, we basically only have 2 responses. We're aware of it cooling or warming, and if we want to know something about the temperature of an object, the exploratory procedure we typically use is static contact. We maximize the contact area of the skin with the object that we're trying to detect the temperature of. And in fact, we can use those cues quite reliably to determine the material composition of objects. So if you hold an object such as copper or stainless steel in the hand, the rate at which the temperature of the skin decreases provides you with sufficient information that you can identify the material composition, as shown by the plots. There are changes in skin temperature. Obviously, most things we encounter in the environment under normal conditions are cooler than skin temperature, which typically varies between about 30 and 35 degrees C. And so it's the decreases in temperature that we're sensing when we identify materials. And over the years, a number of people, including in my lab, have built a number of thermal displays, typically based on Peltier devices, because you can both heat and cool depending on the direction of the current. We servo control the temperature of the display, and we use these displays to understand the basics of human sensing and how we can use that to simulate, for example, grasping a cold or a warm object, or to simulate the changes in the skin temperature associated with grasping objects made from different materials. And we find when we look at the ability to identify materials based on simulating the change in skin temperature, We find that people are as accurate as identifying the material that's presented as a real object and as compared to simulating it with a thermal model of the change in temperature. The point to be made here is that we're not overly good at 55% at identifying real materials by in terms of their composition, but we are as accurate when we simulate those and present those in a thermal display. There's also been work done, Steve Brewster was one of the first working on this, in developing thermal icons by analogy to icons in the visual modality or tactons in the sense of touch. And here we're just exploring the domain of using temperature to encode aspects of communication. And you can encode things such as proximity. People have explored doing presenting effective responses, preferences, and then just using it as a scalar variable, increases or decreases in something such as pressure or flow. And basically the dimensions that we have available to create thermal icons are cooling or warming. We can make things larger or smaller, so we can use the spatial aspects of the stimulus by having either larger LTE devices in our display or a larger number of them. We can change the amplitude of temperature change of either cooling or warming and the rate at which that changes, and then how long we present those thermal cues. And collectively, that gives us a basis for building these thermal icons that we can then explore in a range of applications. And so people have looked at things such as presenting thermal feedback to enhance communication to do with pleasantness or unpleasantness, arousal, in context of text messages or some communication on mobile device. Some people have explored them using in driving scenarios, easy to mount on the steering wheel, and looking at what you can communicate using thermal cues. And we've been looking at creating more realistic sensations of texture by having warmth in collaboration with vibration to sort of enhance perception, so it becomes much more a multimodal sensation. We've also done some linear system deprecation experiments, and here the objective was really to sort of move to the point where we knew what we presented to the person, what the change in temperature would be a priori, so we then could design specific waveforms in order to present a known thermal profile, and found that we can quite accurately represent the response of the skin to a thermal input using a linear dynamic model. We've then worked more recently on incorporating both thermal and tactile cues in a single display in the context, again, of trying to sort of make the thermal input enhance both the perception of the vibration input and make a more realistic perception in the context of virtual environments. Now, one of the problems or one of the issues that one needs to be aware of in combining tactile and thermal signals is that they have very different temporal properties. So if we look at just basic properties such as how quickly information from the periphery reaches the brain, information from tactile receptors in the skin travel along A beta fibers, which have much faster conduction velocity than the fibers that come from cold receptors in the skin, which are either A delta or C fibers. And then in turn, information from cold sensors in the skin travels more quickly into the cortex than information from warm receptors. And so those sort of differences mean that when we try and couple things together, we need to be aware that they're not all arriving simultaneously. And obviously, on the basis of our history, manipulating things in the environment, we've compensated for that, but we get into some sticky points when we start trying to put them all together in the context of a VE. The other thing that we need to be aware of is that due to thermal inertia, when you present information on a display shown in the blue lines in these plots and look at the response of the skin, there is both a delay in the response of the skin to the thermal input and then in the gain. So in other words, if you have a time varying profile, the skin will typically not match that, the peaks and the troughs of that profile, unless you have it over a very long time scale. And here we're even going up to 10, 12 seconds, and you can see the difference in the response of the skin in comparison to what's being presented by a display on the skin. So there's a profound difference between the sensors and the time taken to process information, and then the concurrent inputs are processed on different time scales. So we've also looked at, this is work done by the co-author on the paper, Xin Li Ho, at how people identify warm and cold sensing, sensory changes in the skin. And here the task was, it was either a sinusoidal or a half wave form, and people had to, that was repeated through time, and people had to say when the physical onset of that stimulus was, and in a separate experiment, what the subjective peak was. And there were differences in terms of warmth and cold, with the onset being detected more rapidly with cold versus warmth, consistent with what I've said about the differences in the conduction velocities, the time taken to reach the cerebral cortex. And the subjective peak was delayed for warmth as compared to cold. And so people anticipated the warm peak, but did not do so for cold. And it appeared to also be the case when they started modeling the data, that the sense of cold is more transient than the sense of warmth. So in other words, it peaks and dies away more rapidly than the sense of warmth, which was a very useful thing to find out in terms of some of the results I've just described. There's also something else to bear in mind when we're trying to couple tactile and thermal inputs, perhaps in the context of a glove or a display that's mounted on the palm of the hand, that although the fingertips are the most tactually sensitive region of the skin, thermal sensing capabilities there are inferior to locations more proximally down towards the wrist and the forearm. And so what that means is that thermal thresholds, both for cold and warmth, are higher on the index finger as compared to the thenar eminence, this muscular region at the base of the thumb, and the thenar eminence is about the same as the forearm and the wrist. So in other words, although for tactile sensing we have this proximal to distal gradient in sensitivity, for thermal sensing we have this distal to proximal gradient in sensitivity. And although you may sort of not think about this, sometimes if we want to sense temperature if someone has a fever or infant baby bottle, and you want to test the temperature of the milk or the formula in the bottle, people will typically use the wrist. They'll do this and they won't do this. And so I think that's sort of something that we've intuitively picked up, that actually this skin here is in fact more thermally sensitive than the thicker leber skin on the hand. Also, when we've looked at what we consider suprathreshold events, in other words, if you have thermal patterns, I've just got 4 representative ones here, where there are 2 pulses or a step function, and you're asking and you're just asking people to identify what the pattern of thermal stimulation is, you again find that the thenar eminence and the wrist are more, you're better able to identify patterns presented there than patterns presented on the index finger. So consistently across a whole range of perceptual tasks, we see this distal to proximal gradient. We've also been interested in spatial processes. So what I've just talked about are mainly to do with temporal events and threshold level behavior. We've also tried to understand how well people can localize thermal stimuli. This is really in the context of trying to design displays that optimize how many elements you have in them. So there's a little advantage to having a 30-element Peltier display, and certainly in contrast to what you might argue would be important for having a fingertip tactile display. So in these experiments, we delivered 4 short temperature pulses in a fixed order, either from the elbow going forward to the wrist or the wrist going down to the elbow, using the display schematically represented here. And people just had to give the location of the first 2 pulses that were always delivered at the same location. Again, we either heated or cooled the skin by heating by 6 degrees C, decreasing by 8 degrees C, and the pulses were just 2 seconds long with an interpulse interval of 4 seconds. And then using a GUI on the screen, people just had to indicate the perceived position of the first 2 pulses. They weren't told, obviously, they were always delivered at the same location, but they just had to move the cursor to indicate where along this position scale here they experienced those 2 pulses. And using this format that's been used to study a range of tactile illusions, in which the physical stimuli is shown in the graphs and then the perceived stimuli is shown in the arm schematic, we find that there's more accurate localization of the stimuli delivered near the elbows compared to the wrist. And although the first Cold stimulus, we find there's better location for that when compared to the warm stimulus. The opposite patterns here are cold, the lower are warm. The errors are still around the order of 10 millimeters. However, the perceived location of the second stimulus delivered at the same site changed much more for cold. So if we sort of compare this location to this location than it did for warmth. And that we think is due to that transience factor I mentioned before, that there is, if you like, the warm sensation persists for a longer period of time, and that may have assisted in people perceiving would be an enhanced, if you like, warmth at that location that led them to be more accurate, if you like, in indicating where that one stimulus was delivered. So to conclude, there are spatial disparities that we need to take into account, that when we're combining tactile and thermal inputs in a single display. And maybe one option that we should consider is actually using a distributed display that is optimized for sensitivity. In other words, that there's no reason that we need to co-locate everything. So maybe tactile display, tactile information presented on the glabrous surface of the hand, thermal more proximally along the forearm or on the wrist, and that those can actually become to be fairly coherently perceived to be part of a single representation of an event that is going on in a remote environment. We know that thermal sensors are inferior to the sense of touch at localizing the site of stimulation, but we can always draw thermal stimuli, if you like, to a tactile event. So in other words, it's much more labile sense in terms of identifying where on the skin things occur, but the fact that you have a tactile input coming in means you can actually relate the thermal event to that tactile event. And we need to look at seeing what the subjective simultaneity is for these different perceptual systems. In other words, at what point do I perceive a tactile and a thermal stimulus to be temporally coherent? We know for haptic auditory stimuli, it's in the order of 25 milliseconds. And we are at the moment doing research on trying to work out tactile simultaneity with thermal events. And here we're using pressure, vibration, and skin stretch as our tactile stimuli in order to see if there are any difference between those classes of mechanical stimuli on the skin and warming and cooling. That's it. Thank you.
Time for one or two questions.
Thank you so much. I learned so many things. Could you speak to what kinds of applications you think this kind of stimulus is well suited for, and perhaps what kinds of applications, and interactive applications in which it's best just not to explore, it's not going to work?
So I think for a while people thought that thermal sensing might be good as an alert in a range of situations, and I don't think it's good for that. The thermal sensors are slow in terms of the sort of applications we're looking at, and certainly in the work where we combine vibration and tactile, if you have an intense vibration, it completely masks the tactile. And it's not sensory masking, it's just this big input that's this very gradual increase in temperature. And as you may have noticed, we had, in one of those experiments, 6 degrees increase, but 8 degrees decrease. So you're very quickly, if your skin temperature is around, let's say 35 or so, you don't have a wide margin of heating without going into pain. And some people will experience pain at 40, 42, although most of the textbooks say it's 45. So I think it is much more in the context of enhancing the perception of vibration than of a texture. So it's not that you feel the texture, but you feel it's living texture, if you like. You're simulating an animal, contacting a person. And then with the whole growth, certainly in the COVID area of affective touch, affective technology, incorporating warmth in that, and that would be a very natural application, coupling with something that feels like a caress or a smooth movement across the skin. So I think it's much more in putting them together would be in the context of texture or affective touch displays, or just giving you a more realistic experience. If you have a cave or a big VE where you can have things that might seem like winds and sun, heating, and so on. So, but they're more at the body level. And we also need to bear in mind that the thermoreceptors in the skin are really not there for display technology. They're there for homeostasis to keep the temperature. Your core temperature varies by plus or minus 0.5 degrees C. So large areas of skin being heated and cooled change the thermal load on the body. And so that's summated. So large areas, that becomes a more intense stimulus, thermal stimulus. And that's an important consideration when you think about having a multi-element display. It's adding all those elements. It's as if when you had a bigger visual stimulus, it was brighter. And that's not the case, but the thermal sensor it is.
Maybe I'll take one.
Thank you. It's a really interesting topic. My question is, have you found, vibrotactile feedback usually has to do with heating up technology? Because when the vibrations are generated, we generate heat.
Right.
And have you found any effect, does any threshold changes, for instance, any effect on frequency discrimination or spatial resolution or vibrotactile stimuli
So
related to thermal?
I haven't done that, but I know Bolanowski did that in the 90s. And I mean, because some of these mechanoreceptors are thermally sensitive too. So you need to say, is it due to the change in the response discharge rate of the mechanoreceptors versus thermoreceptors? The one thing that we have found using suprathreshold stimuli is that warming the skin enhances the perception of vibration intensity, which we think is a mechanical effect. So in other words, when you warm the skin, you're changing its viscoelastic properties, you're changing the propagation of the surface waves associated with vibration, and that makes it easier to identify changes in intensity. These were suprathreshold studies, not absolute thresholds. However, it was detrimental effect on encoding frequency. So there are these very specific changes that we sort of are starting to explore in more details that you definitely see. You don't see any effect of cooling over the ranges that we use. I mean, obviously if you get in the low 20s and cooler, that's when your skin starts feeling numb and so on. You would expect to see changes, but certainly over the range that's sort of within the normal range of skin temperatures, we haven't found any effect of cooling, but definitely warming, yes.
In the interest of time, may I suggest we continue the discussion during the break? Thank you. Next. Speaker is Razvan, and he's going to talk about the relationship between frequency and the hand region activated.
All right. Hello, everybody. My name is Razvan, and so much. My name, and together with my two supervisors, Nils and Stefania Serafin, we conducted a study, and I will present you the results of the study. I'll try to be as brief as possible. But first, I would like you to look a little bit at this plot, and I made some highlights. I hope you can see them. This is the total amount of papers dealing with vibrotactile actuators in the last 40 years. And more than 53% of them focus on that. If we include the arm in the hand nomenclature, that would increase to 60%. So it's easy to see that the hand is a very focused area, and it's an important area, mostly for the perceptual property that it has. All right, so because the hand is one of the most used areas for tactile augmentation, we thought it's a very interesting idea to try to map the perceived frequency response of the hand. So to do that is to ask the question: does frequency influence the region of the hand where one receives tactile stimulation the most? So how does frequency, first of all, is frequency actually influencing where you tactile stimulation? And the answer is yes, according to the study that I will present in a second. All right, before I present you the study, I'll present you the materials. This is the device that we call it a VAM, a very bad naming scheme. It's called a Vibrotactile Actuated for music. This is the best naming I could do. And it's built around the Tactfeature BM1C. This is a voice coil actuator. It has a very wide frequency response. And the resonant frequencies, which are around 300 Hertz, can easily be tamed. And I will show you what we did to achieve that. And it's built around this handing wrist splint, hand wrist splint, which is a device that you get to wear when you have the opportunity to break a wrist. So that device minimizes the tension in the wrist, and the tonus kind of lets the hand rest in this position. And this device is modeled around that, so you use the least amount of pressure to hold it in an attempt to kind of control the pressure that users will have on the device. All right. In order to see, to kind of flatten the frequency response of the device, we did 2 filters, and we did some measurements, selection of measurements of the frequency response of the device in multiple spots, and then we averaged the filter, and then we did another filter which tries to inverse the frequency response of the hand, as known from literature. So these 2 filters combined resulted in this filter, which it's not that extreme. It's only like 6 dB of amplification at some low frequencies, and you can see 200 Hertz with a little bit of attenuation, 1 dB of attenuation. So all the signals that have been presented to users have been passed through these 2 filters, and we run 2 experiments, and mainly because the experiment 1 gave us very good results, and was like, wait a minute, what if the position of the actuator actually matters? So we removed the actuator, and we ran the same study again, and the results did not change much, which was great. And I'll tell you a little bit about the experiment. The hypothesis is that people perceive distinct frequencies in different regions of the hand, for example, like a thumb, tip of the finger, phalanx, the palm, wrist, when stimulated by a single actuator, vibrotactile handheld device with a constant subthreshold amplitude. These are the frequencies that they have been presented to. They're third with 3 semitones apart in between the 0 to 1 kilohertz range, 15 in this case. It's mainly focused on the Pacinian receptors, which is the one that gave us the most information about the vibrotactile sensation. And yeah, this major third is the just noticeable difference in literature by Carl Hopkins. So this was the experiment layout. People were presented with a computer. They were supposed to hold the device at the left hand, the mouse at the right hand, the pad to decouple the hand from the table, foamy pad, and they were asked to find a comfortable position, and they were presented to the stimuli 3 times per stimuli in the random order, and they were asked to select one of these areas that they have felt it the most. They were actually asked to feel 3 areas and to rank them, but because of the post-experiment interviews, the ranking scheme did not really seem to be consistent. Everybody was, or the people that were interviewed were, yeah, I felt this one the most, and then the other 2 that I remembered. So we disregarded the order, and we just used it as nominal data with equal value. So there were 2 seconds for each signal using a sine wave, and we had 32 participants for the first experiment and 35 for the first, 32 for the second. I'll quickly go over the results. All right, so these are the results. These are just some heat maps of the results, and you'll see that it's pretty hard to understand, or at least it is for me. We have something happening at 76 Hertz in one experiment 1, not so much in experiment 2. But what is easy to see is that in experiment 1, the thumb is a lot more actuated than, let's say, the pinky in this area. And in experiment 2, we have the base of the fingers, which is mostly actuated. And this is something that has to do with the position of the actuator. If I go back to those two graphs. So experiment 1, the thumb is hold the device be the closest in contact with actuator, and the second experiment, the bottom of the fingers would be the one closest. But then again, it's very hard to conclude statistically out of these. So what we try to do is put this into a multinomial regression model, and we basically try to predict the chance of selecting any of the category by the explanatory variable, and in this case, the only explanatory variable would be the frequency. And while this, so in the left, this is experiment 1. I'll show you another graph, experiment 2. In the left, we have the empirical data, and on the right, we have the prediction model. I removed some of the areas to declutter, so if there was no significant change, they're not on these graphs. So not all areas have or the effect of frequency is not visible on all areas, but some areas can be, in some areas can be seen very clearly. And to give you a quick reminder, the letter U means not sensed. The area is not sensed, so we can see that the prediction skyrockets after 800 Hertz. And Y, X, and O, let's look at Y, X, and O, would mean that we have the Y in the tip of the thumb, X here, and O over here. And they decrease, so the chance of selecting those decreases with frequency, with increasing in frequency, which means that for the first experiment, when the actuator was closest to the thumb, the physical location of the actuator matters less with increasing frequency. And then we see that an increase in probability for areas, I'm not going to go back to the slide, but I'll tell you that the areas that are closer to the fingertips have an increased effect with frequency. And this is the same thing that we can see in the second experiment. Again, letter O was the one over here. So you can see that the effect of the actuator's position decreases with increasing frequency. And Y was this point, H was this point, D was this point. So again, the area has fingertips increases with the probability of selecting one of those areas increases with frequency. So this is a positive outcome, but it would be very easy to look at those graphs and try to look at a case-by-case study. But because of the limited amount of data for each individual frequency, which was 3 per participant, we cannot conclude that, yes, this frequency is having a higher chance of being selected at this particular area. But instead, what I did was to create 2 models, one that has these 2 models, and compare whether the effects of the frequency explain the changes. So basically, there's 2 data sets, and if there's a statistical difference between them, that can only be explained by frequency. And just a simple ANOVA test, the p-value was below machine learning. So yes, frequency influences the perceived area in the hand. But looking at those graphs, we can only get like an indication of what would be the case. We need a lot more data for each area independently to be able to conclude that one of the areas would be more susceptible to be perceived one particular frequency. But yes, I think this was my talk. If you would like to talk more about my study and whatever we do in the multisensory experience lab, catch you in the break, I guess.
Thank you.
Thank you very much.
Right, thanks for really interesting talk. Just a small question. I was just wondering what led you to divide the hand into those specific regions?
Luckily, I didn't have to. Like, they come from a biology book, and they all have a name. So I would not try to say all those names, but they do have names. So in an from an anatomical point of view, all these regions have a name and a product. So I did not do the segregation. Yeah.
Thank you.
Shall
You're having the actuator and then you're having plastic or some kind of material. Yes. Unfortunately, that will vibrate. Which would be part of your, because you're only talking about the frequency and the placement of the actuator and the hand, and I'm guessing that the response of that thing will also change with frequency.
Yes, but we measured it. We measured it in 3 locations, 3 times per location, and we did a filter to compensate for the frequency response of the device.
Yeah.
And then, this is the filter that we applied. At least we attempted to minimize the effects of the resonance of the device itself.
take one more question.
You also consider checking the contact. So contact was stable, so like for the next stage, if you consider capacitive sensing to, because I believe it wasn't as much in contact. But could also be correlated as well.
Very much. The only attempt was to try to use a little force to have a consistent amount of force required to use. So that was the only attempt that we did. I strongly agree with you that some areas would definitely lessen contact than others, and quantifying that and trying to introduce it in the model and see if those have also an effect. Maybe they can explain the frequency changes. For example, the area P, Q, and U were never selected. They have so little data points that my model did not converge. So I just had to make one area out of those in order to get convergence within a sensible number of iterations. So yes, I think further studies will have to have some sort of contact checking, pressure check.
All right, you get to ask one more.
Yes, I agree with it. So, did you actually try to maybe, aggregate some of these regions and like calculate a new model with less variables?
Yes, I did, and there's 2 discussions that I had in my head and my supervisor. How should we do it by distribution of Pacinian receptors? Should we do it by fingers? Should we do it anatomical? Should we do it by the results that we have? So we could not find a consensus of what would be the best aggregation. If we try to differentiate fingers, does it make sense to ask that question, right? And we couldn't figure out what would be the best aggregation. In my head would be, let's try to do it by the distribution of Pacinian receptors and see if we can explain this behavior through that, but previous literature did not indicate that that could be the case. So we tried to have that discussion, but we didn't figure out what would be the best approach.
Thank you.
Yeah, I'm sorry, maybe we'll continue during the break. Let's thank the speaker. Last speaker of this session is Clinton. His talk is on perceptual evaluation of the quantization level of a vibrotactile signal.
I work at the university in the region of Characterise. And today we'll speak about the perceptual elevation of quantization level of robotics. R3 are both projects funded by the French National Academy, named Speculative, which are engineering, psychologists, and musicologists are involved and try to use Vibrotactile signals are sensory feedback and communication channel during musical practice. In order to play Vibrotactile signal, we use digital version on our computer, send it on the sound card, and an amplifier, and at the end on the vibrator. So we play Vibrotactile signal as we play audio signal. That's why we should consider two fundamental aspects, which is sampling frequency and the number of quantization. In order to play audio signals, you can use this kind of sound card, which has a sampling frequency of 44 kilohertz, and because it's twice the maximum frequency human can hear. And there are a number of quantization bits of 24. For the touch, we can reduce the sampling frequency to 2 kilohertz, but we don't know how many quantization bits used. That's what we try to know how many bits of quantization should be used as minimum in order to make the digitization of vibrotactile signals perceptible. We found in the literature some 8-bit vibrotactile devices. So if you try to imagine what is 8-bit signals, you should know 16-bit signals sounds like audio CD. 8-bit signals sounds like MP3. So you agree that a digitization on 8 bits will reduce the audio perceptibly, the audio quality of a signal. Okay. So we should know if we reduce perceptibly the quality of our tactile signals when we use 8-bit digitization. Our hypothesis is the quality won't be reduced, and if it's true, we can stop to use this kind of sound card, and we will be allowed to directly play vibrotactile signals with this kind of equipment, Raspberry, or directly 8-bit digital analog converter. So to test it, we will make a pairwise comparison in which the two signals have always the same waveform, the same frequency, same amplitude. Actually, only the number of quantization bits will change between them. We will use sine wave because it's a simpler signal we can use. And the frequency of this sine wave firstly will be 225 hertz because it's a frequency to which our skin is the most sensitive. We will also use 45 hertz frequency because we are less sensitive at this frequency. But with the preliminary tests, we find it's easier to perceive the quantization effect or the digitization effect at this frequency. And we will use 135 hertz because it gives intermediate behavior. For the number of quantization bits, we will use 16 bits for the quantization because it can consider as a pseudo analog. With the preliminary test, we find it can't make the difference. It cannot make the difference between an analog signals and the 16 bits signals. Of course. We will use 8-bit signals in order to check our hypothesis. And to find a threshold of perceptual digitization effect, we use 4 and 2 bits. So we have 30 pairs of signals there. Participants will compare all these pairs twice in a random order. For the comparison, we will put the vibrator in a bracelet, and we will fix the bracelet on the inside of the wrist. And the participant has this kind of interface with 2 keys, A and B, which play the signal E and B. And the participant should tell us to perceive the signals are the same or not. During all the experiments, the participant wear earplugs, headphones in which white noise is playing in order to avoid here the liberator. At the end of the experience, we can just have access to all the results of the participants, and we can combine or merge the results of all the response of all the participants, and compute for each pair the similarity index, which is the number of response same signals on the total number of presentation. So similarity index of 0 means the signals are always perceived as different. And similarity index of 1 means the signals are always perceived as not different. So now for each frequency and each pair, the similarity index, we can discuss that after, but I firstly say that the mean value for pair of same signals is mean value of the similarity index is 0.77. And on the other case, for 45 Hz, we can clearly recognize 2-bit signals, but that's all. It's also true at 125 Hz, but at 225 Hz, you cannot make the difference between 2-bit signals and the direct signal. So to answer the previous question, the response is it depends on which frequency you try to digitize, but you should probably use between 2 and 4 bits for the quantization. Now I will quickly describe the effect of quantization with this kind of analog signal in blue in blue. You have on the output the arranged signals. Here is on 2 bits. So the digitization will introduce this kind of steps, and the size of the steps depends on the number of bits used. The more bits used, the less the smaller the steps will be. Actually, these steps introduce harmonics in the spectrum of the signals. We can quantify these harmonics with the THD, which is the sum of the power of the harmonics on the power of the fundamental tip. And so if the THD is 0, that means we have an analog signal. It does not introduce any effect of quantization. And if THD is more than 0, you have to introduce quantization. So for each signals, I can compute the THD, and in each pair, I can compute the difference of THD, maybe it's delta THD. And now I can represent each pair of signals by a dot on a graph, with on the first axis delta THD, and on the other axis the similarity index. Sorry. So for low THD index value, I have high similarity indexes. So if the signals are the same, I perceive it as the same. But with high THD, I can have low or high similarity indexes. So the THD cannot predict the value of the similarity index. It's probably due to that the THD does not take into account the sensitivity of the skin. So we try, when you have to do the THD, first you should compute 50. And before, so we computed the 50, and we apply a gain on each amplitude. The value of the gain is based on our sensitivity. So if we are sensitive at this frequency, we will apply a high gain, and if we are not sensitive at this frequency, we will apply a low gain. So for this spectrum in input, we have this one on output. And our hypothesis is that this spectrum represents our perception of this spectrum laid on the skin. So now, if we compute the THD on this spectrum, we have like a THD, a perceptual total harmonic distortion, which is just a THD with the gain in front of each. And we can compute the delta THD, the difference of THD. Like before, with the THD, I had this, and now if I use a PTHD, I have this one. So now it's the same way. Now the PTHD seems to be able to predict the value of the similarity index when you have to compare pair, and there are threshold, or it seems to have the threshold around 35 of the delta PTHD. So it's a threshold of perception. Is a threshold of the perceptual quantization. And like we so there are some limits to this one. We can reproduce this experiment with more points in the area of the threshold. We can repeat it with more frequency. We can test the robustness of the PTHD with more complex signals. Here we have used just sine wave. We can use a threshold curve based on the wrists in order to calculate the gain of the PTHD, because we have used the threshold here made on the finger. So we can take on the wrist. We can repeat it on other parts of the body, and we can take into account the mechanical behavior of the actuated. To conclude, it seems that Vibrotactile signals can be digitized on 8 bits without introducing multiple digitizing effects. The THD is not efficient in order to predict the versatility of the digitizing effects, but the PTHD seems to be. Thank you.
It's very interesting. The number of quantification, the number of beats, it's also really related to the dynamic range. So we're using the 16 beat because that's 96 dB. And that means that if we have a pure tone at 80 dB, it's 16 beats, the noise will be at -10. But if we present, I'm still talking about audio, a pure tone with 8 beats at 60 dB SPL, noise will be around 5-6 dB, and you will not perceive it. So at presentation level of 60 dB SPL, you will not perceive the difference between 8 beats or 16 beats or each. So therefore, my point is that the level of presentation is very important, because that means that what you're going to perceive is this quantification. So if you redo your experiment with the huge current, you might perceive the quantification. So how did you set up that parameters in your experiment?
There are 2 points. So the first one, you can show it, observe it in this graph. The dynamic will be always the same between each quantization level. Actually, the higher level obtained was 1, the lower 0, and we bet like allowed value in them. And the number, just the number of allowed value, we change according to the number of it's used. Right? So the dynamic was always the same, and we use the level of Vibrotactile signals was always around the threshold. Yeah, that's good.
Actually, can I ask you to go to the next slide, right next to the end?
This one.
The very last one. No, the Varelo law.
This one.
Yeah. I'm just looking at the upper left at the highest point versus the bottom point and see what the dynamic range is. The 60, 70, 80, close to.
I mean, in audio, I know what's the highest one is the level of pain.
Yeah, this
Where
is
you
different
get
from
Is
audio.
that the level where you feel pain or you don't? That's different.
Yeah, around 55, sensation becomes painful, but at low frequency, it just means very large movement. I think starting at the vibration range is when it gets too intense, right? I think that's why we stop at 55. Anyway, so my related question is, all this conversion to PTHD and all that, what you're essentially doing is compensate for different sensitivity, right? I'm wondering if your experiment should just focus on the most lowest threshold, because that really determines what the detection is. Does that make sense? Because you're essentially just converting, equalizing sensitivity with your PTHD. Yeah, so the noticeability is really determined by the most sensitive frequency.
So I understand that.
Okay, so another way of saying this is that the quantization noise is linear, right? I mean, right, but this is a log scale. So at the most sensitive frequency, you will be able to pick up the quantization noise most readily. Sorry, we'll discuss that later.
Sorry.
Yeah, I don't want to take up too much time. Any other questions?
I inquire about your selection of the frequencies. You said that you selected upper and lower ends for maximal and minimal sensitivity, right? So my question was then, why? Could you explain why you selected the central frequency as halfway between the frequencies as opposed to halfway between the sensitivity levels?
Sorry, I didn't hear the.
Why did you select the central frequency as halfway between the two frequency values as opposed to halfway between the sensitivities?
Okay. I choose. So yeah, it's the frequency at which we are the less and at which we are the most sensitive. But also, I reflect about the digitization will be perceptible or not. Because, for example, I didn't explain that. With the digitization, you will introduce harmonies. But the first harmonies you will introduce is third, 3 times your fundamentals. Okay. So you are sensitive between 10 Hertz and 1 kilohertz. So if you choose signals around, let's say, 400 Hertz, quantization effect will be to introduce harmonics upper than you can feel Vibrotactile. With this. Did I respond to you?
So I'll ask you later, smart one.
Okay, I'm sorry.
Okay, we'll continue the discussion. Yeah, thank you so much. That concludes our session, and let's give another round of applause to all the speakers.
So welcome to the second keynote, first of our Magnusson will talk. He's an associate professor in CERTE, Rehabilitation Engineering and Design at Lund University, Sweden. And he has two main areas of interest. The first is concerned with non-visual interaction design and how to use senses other than visual in application and services. And the second is design and design methodology for person with and without disabilities. Charlotte is also an experienced programmer and with particular experience from in interactive multimodal applications. She has led and participated in several Swedish and European research projects, and she was chair of the 7th HAID in 2012. Charlotte is a member of the Swedish Braille Authority and of Working Group 9, Tactile and Haptic Interaction of ISO, which is the International Organization for Standardization. So let's welcome Charlotte.
Thank you very much. It's great to be here. I'm feeling that this will be kind of a switch from the previous session where it was very, very specialized. I sometimes feel that you often hear this, that when you're a scientist, you know very, very much about very, very little. And I feel that we work a lot with design projects in different areas, which sort of leaves me as a person who knows maybe not so very much about a wide range of topics. So actually, when I got the question to talk here, it was a little, what should I talk about? But I realized that the core of everything that we do through all these projects that I've been part of is basically working with users and co-designs. So I kind of decided on that. And the group I'm part of, we focus quite a bit on accessibility and design for all. And of course, working together with users. So I've been at the same place for a long time now. It feels almost embarrassingly long, but it is a very nice place to be. I've never really felt the need to go elsewhere. I might come back to that because we currently have a postdoc open. So if anyone is interested in the 2-year postdoc plan, the application closes 1st of September, so it's quite short still. So we do research on both accessible and inclusive design. So we do the design for all things, which is supposed to, where you target basically everyone, but also specific accessibility projects. And I also put this Swedish Braille Authority, which is sort of interesting because I actually don't read Braille. But I'm there basically because we've done work on tactile images and that sort of thing. So my plan for this talk is to talk a little bit about co-design and then sort of expand through a lot of examples from projects that we've done and end up with some discussion and conclusion. And I sort of have a feeling I have too many slides, so I might skip over a few, but I'll do my best. And if you wonder why the cats are there, it's more about appropriating designs in this case. Often when you design something, you find that the users will appropriate it and they will use it in a different way to what you had intended. And in this cat, this is flower pots, and of course, very good cat pets. So the first thing when you talk about design, I think is this observation, and we heard that already in the keynote yesterday, this thing about building in values, and we always do that. We build in our values and the way we think about people and systems in the kind of tech we build. And my example is well, maybe the one I usually take for this is, because I think it's a very clear example, and this is now quite a few years ago, the head of our group uses a wheelchair. And we were going, as a bunch of people, we were going to Stockholm to talk, future collaborations with the research group in Stockholm. And I thought, well, I'd be environmentally friendly, I do the train. And then typically on these trains in Sweden, when you do work things, you go first class, because first class is not very much more expensive than the second class, but you have more space and it's good for working and you have the Wi-Fi and everything. So I booked first class. And then it turns out that no, the persons who have designed this system, they have decided that a person in a wheelchair you cannot go first class. There is one wheelchair seat in the train, and that is in the family wagon next to the toilets. And that says very much about how those persons involved in this, designing this system, have been thinking about, well, persons in wheelchairs. So it's sort of important to think about what you build into your system. And of course, I think all of you do design processes, so you know that when we work with this, it's not just, oh yes, have this idea, build it, finish. It's actually a process. And of course, it is important that somewhere along the line you involve the persons who are going to use your stuff. And it's not, of course, a sufficient condition. I mean, you can still do really bad designs even if you involve your users. It's just that hopefully, I would say it's it's not as sufficient. It's a necessary condition because it will rule out some of the worst things that you could do, the really wrong things. But at the same time, you could still not get the best. I mean, you still need to do other things as well. It's not just about involving users. I've been on some design discussion lists where people are like, yeah, we use a set of design, doesn't solve everything. No, of course it doesn't. You have to be a good designer as well. So things that are important, whatever, I mean, you can do different design processes can look a little bit different, but that you have the user involvement, and also that you have, I'd say, when you're doing real things, you actually need real contexts and activities. It's a big difference on what happens in the lab and in the reality sometimes. And also, I know I have an engineering background, so I know that as an engineer, you tend to be problem-oriented. You love problems because you want to solve them. But it is a good thing to at least think about focusing maybe on opportunities and abilities instead of just problems and disabilities. And I also have this picture when you're working with users. This is actually from a colleague of mine. We used to have this one, like, so nice to think about trying, because when you come in as a researcher, you're always coming from a position of power, but you try to balance and be manage things so that you're kind of at the same level, so that you're not the big guy who knows best. And yeah, you have the users there that they will basically tell you what to hear, which of course you can set up things so that that happens. I took this one just because I think it's a nice, it's a guy called Stefan Johansson, who's worked a lot with cognitive impairments and also homeless people. And he also works at an organization called the Gripsam, and they have an ethical framework, which I sort of think is a nice reminder. You can find it in his thesis, Design for Participation and Inclusion Will Follow, Disabled People and the Digital Society. I think you Google for that and you find it. And it has these points like act in the spirits of conviviality, be nice, basically. But also solidarity. But, you know, be pragmatic, do the stuff you can. You can't solve everything every time. Be practical. And of course, democracy, citizenship is important to think about. And don't design for the diagnosis if you work with accessibilities, because a diagnose is a medical thing, and it says often very little about what the person actually can do. And well, I think the example for don't be surprised when people have needs according to difficulties is like, for example, if you're homeless people and you send letters, where do you send letters? Maybe banking, whatever. I mean, you have to kind of understand your users, and don't patronize, and don't treat people as vulnerable. And of course, this goes into with the emancipation and power relations and trying to enable people. kind of like this point more or lower. I haven't run into it specifically, but yeah, do the right thing. It's what he says. Kind of. This I think is a good thing. Is that you think about participation. You think about how do we actually participate in stuff. The inclusion will follow, and it is okay to be wrong. Think twice. I mean, that's one of the things. I know I had this discussion yesterday with someone saying that it's kind of harder to get your failures published. Of course it is, but actually often the failures can be the most useful because that is where you really learn things. And there are also some things like being sustainable, sustainability, accessibility, and also this thing about if you want to build something specific or use mainstream. I mean, generally it's good to have mainstream because it's there, and actually bringing a new product to the market takes time. But of course, there are specific problems with mainstream stuff as well, which will come in the examples. And then, take what help you can get. Use your guiding stars, whatever conventions, standard guidelines, other examples, whatever. So I had before, when I was saying that real activities, and again, I have this kind of example from my colleague. He says, since he uses a manual wheelchair, he says that, you can have this place that is perfectly accessible, but if you have a conference mingle, which is an activity that is designed in this accessible space, the activity itself can be designed so that it's actually not very good. So he says he always hates conference meetings, this kind of standing around, because first of all, in your wheelchair, you're on this level, everybody else is up here. The second thing is that if you have a glass of wine in one hand, you can go in circles, and if you have food, you're stuck. So it's really important to have seating, and I think for people like me, I have bad hips and bad knees. I also like seating in this experience. So it's a lot when you're thinking general and design and activities. I mean, yes, you need to think about what the activity is as well. And of course, real use is again about the activity. I kind of say bad examples. So this thing is a device where it feels like they've never really actually tested this in real use. It's water faucets. So you wash your hands with a sensor under, and then you have this air thing on the sides. So it actually blows air very strongly on the sides to dry your hands. The thing is that after you wash your hands, there will be water in the sink. So when the air comes down, it doesn't work. So real use is important. And I think for all of us, we have this implicit reference that it's important to be aware of, that a lot of our design and our design decisions and things we do take place in office spaces. And especially, I noticed that myself because I do a bit of like interaction design programming, and we work with vibrations, and then you set the level of the vibration, you think, oh, okay, this is going to be really good, and then you think this is so strong, and you go out and walk, and all of a sudden you can't feel it because it's not strong enough, because you have all these extra vibrations when you're walking around. Again, since I'm talking about co-design and it's audio haptic, and from my point of view, some of the work has been with vision impairments, for example. I mean, the method, if you're talking participatory design, co-design, or the design methods you have, that they're not really the problem. The problem is kind of getting the activities and the materials right. Because a lot of the design tools we use, well, you have post-it notes, drawings, cards, videos, paper prototypes. First of all, they tend to be very visual. And secondly, they're also very screen-oriented. You're taking this, oh, I have a paper and I draw a picture. You do haptic stuff, you don't want that, I guess. And so I'm just putting this if you're interested in different types of methods and ways to do this. We had an EU project now, kind of nice, but it was some time ago, and we actually tried to make a fairly nice overview. We still use it in our teaching, so that I think the method descriptions are still okay. The references in it are getting old, but it's this kind of you have one, not one page, but 2 pages per method with some, and then you have a lot of methods as well. It's kind of a nice text. I think you find it if you search for it. So now I'll see where I am with the time. Still quite well. When am I supposed to finish?
So, about 30.
In about 30 minutes. Okay. So I'll move over to the practical examples and talk around those. So the first example is actually from a project which I didn't work in. It was my colleagues. It was a very interesting project to follow. They work with interactive Snoozelen environments. I don't know if you know what those are. That's sensory stimulation environments for persons with fairly severe and often multiple disabilities. And I'm usually taking this one just as an example, because sometimes you hear that can all users be involved in design? And I think this is kind of a good example of very, you say maybe difficult, or this at first thought very difficult group to work with, because the persons there typically don't have language, for example, and as I said, fairly severe disabilities. So this is an example that everyone actually can participate in design. And in that project, I know they worked very much looking for what they call design openings. One example, I think I skipped that one, that was an interactive water bath, was that because we worked together with these kind of places, and the staff there said, oh, we have this guy, and all he does is he just hugs things. He always hugs things. And that then was a design opportunity. Yeah, design something for hugging. Let's see. So this is a research colleague. So this design here was, there was a Kinect inside this big. You see how much that is something that at least as ordinary interaction design, you think, oh, hands, but actually, face and the mouth. I think I'm stopping there. It's also been interesting to have this one at conferences, because it's been, it's not just these kids who think it's cool to play with. Everyone thinks it's cool to play with. And here is another one, which I think is an interactive button, where the surface of the button is where you interact. It has, I'm going to stop there. But there you see, I don't know, do you see? I can see here, but there is this putting the face again against it. But the design has, I think that's hard to see. It's kind of a big box, and then it has like a paper, and under the paper there are these metal spirals that rotate, and it feels kind of alive when you touch it. So it's really a cool feeling. And we had it in a workshop also with blankets later, instance, and yeah, I mean, one of the children loved it so much, it was almost like a disaster to take it away. So the important points, I'm trying to look at the points that were important in this process was, first of all, for inspiration, there was a lot of video documentation, looking for this kind of, looking at the video together with the staff and finding the design opening. But in order to get the children to actually, you know, control or be part of the process, there was a lot of building and testing. So because things, and you think even if you don't have language, it's very easy to show that I don't want it, or move away, or not engage. So it's kind of obvious, I think. I mean, you can get a lot through how people respond, even if they're not able to tell you. And one design quality, which I think comes in actually many of our projects, is this thing. The guy who wrote this, his thesis is tangible participation, engaging designs and design engagements in pedagogical praxis. Henrik Sverlarsson, he's Danish. So he uses this Danish word called væsen, which kind of means spirit or aliveness. It's a quality in the haptics, and if you can really get your haptic system to feel a little bit alive, very often it's pleasant, it's nice to interact with. And I'll come back to that. So if you want to look at more videos and things, there is, I think it's still active, the website. And it's so now I'm going over to I realized that I didn't do any slides on phantoms. We have done several projects actually with phantoms. But so this is kind of the only slide on that. It's because a problem when you work with that kind of haptics is how do you lo-fi prototype? And I think that goes for a lot of the haptic systems is, well, you know, you have to actually feel it. You need often something that is very finished, which means that you do a lot of work and then it's kind of embarrassing to find out that none of that didn't work. So Lego is one of these materials that you can use to do haptic lo-fi prototyping. And in this case, it was a master thesis student actually who was looking into how you control your avatar with the phantom and discussing that with the users before actually implementing it. Was a haptic, a game using the phantom. I'm just assuming that everybody knows what the phantom is. Is there anybody who doesn't know the phantom? Okay, so the phantom is, sorry, it's kind of a robot that where you hold a pen and the motors in the robot will resist you when there is something. So it's kind of like touching the world with the pen. And there was, it's sort of interesting also, you see how things go in research, because now this is now, I think 30 years ago, early 2000s, there was a lot of phantom work and research and things. But then when the mobile things came, people just moved because this is a desktop system. Because they'll buy it, but it's called GeoMagic Touch these days. So the next example is a project called Tactile, and that was an EU project which I was coordinating, and that was a 4-year project. So of course, EU project 4-year, you can do a lot of stuff. So we did many things, many different user activities in that project. And the aim of the project was making this very visual thing at the time, you know, maps and navigation information, making that more visible, or not visible, making it accessible through other senses than vision. So we did, for example, hands-on design workshops with a whole series of activities, like first focus groups, and then often when you do, you want to have like a co-design workshop, you want to prime people a little bit beforehand. So you do something, we did diaries, just, I mean, we didn't much look at the diaries. We did, but they didn't give us that much. So the main focus there was actually to prime for the activities you think about it beforehand. And then we had made little, this is kind of some rubber material you can buy at hobby shops, and we had glued it together to at the time this workshop was, this was kind of what mobile devices might look like. And we had materials for mimicking earphones, wristbands, cables, etc. And asked our participants basically to design a navigation service for us that worked the way they wanted it to work. And they then presented, you know, Wizard of Oz kind of walk where they explained how things were supposed to work. Another activity which was actually really, really useful, at least maybe it's because we were looking at navigation services, but still, we basically had a person play the device, and the participant then, there was a task he was supposed to do, and the person could ask for advice at certain points, or when they needed it, basically. And we saved those questions and then used them in the design process. And of course, I think anyone who has worked with mobile devices know, and especially if it's outdoor stuff, you know that weather is an issue. So we thought, yes, and this was going, because in projects you never know. You often plan them generic month 1 and month 8 and whatever, and you end up having to do these things, in our case, in November, December in Sweden, which is not a good time to be outdoor. So we thought, yes, go into a mall. And that worked, but it had some problems with documentation, because you couldn't, we weren't allowed to video film. I think you're typically not allowed to video film in malls. And we could take photos as long as we didn't photo the ceiling. I think that was some sort of security thing. And we also noticed that when we just piloted, we walked with, you know, a notebook, took notes after and followed, and that got so much attention. So what we actually did in the final was that we used our mobile phones and just recorded the audio. And it gave us a lot of really useful information. So I think that was a good thing. When you work with interaction design, I mean, what we were interested in was how to show the way. The thing is, of course, that you can't just ask people, you need to have some place to go. So what we ended up doing was some kind of tourist walk. Sounds and haptics. Just going to show a very short. So basically, you scan with your phone, and when you point it in the right direction, it vibrates, and it gets more intense as you get closer. Yeah, and I think I have not so much time. So when you walk, actually, you will hear like what we call time windows from the past. It was like a story. So I'm going to go up because I wanted to come back to the aliveness, but I guess first I should say that basically in this process, the important points were we started out with this idea workshops. We also, because this was kind of a new type of interactions, we did a very controlled studies on how wide the angle is, because if you have a very small angle, you will miss it. So you have to have some sort of angle, and it's surprisingly wide, like 60 degrees work nice, and it feels like, yes, I'm going in the right direction. And then we did smaller, more qualitative studies in context with users. So we walked a lot downtown Lund, which is a nice place to be, both with and without tech. And one thing which I think actually was very good for us was that we started with the non-visual design and then added the visual information, because this was a system that was supposed to be for everyone. So we had to have visual information, because very often you do it the other way around. You start with the visual and then you add the haptics, but actually starting from the haptics was and haptics audio was a good thing. It turned out that the resulting application then, there are local museums in Sweden more like, they're run by volunteers, and they have this organization, and they kind of gave this. There is a small company who's using. So it's kind of evolving. It's very nice when you do stuff and it actually gets out into the real world. But coming back to the aliveness, I mean, since in this project, we had this kind of pointing the phone and doing, and then some of the first prototypes, they were very engineering, like they were neat, and which was so annoying. But if you make it a little bit more like more alive or a little bit like heartbeat, maybe something like that, it's much more. I mean, it's okay. It feels like more natural and gives a much better feeling. This is again another project. See how many slides I have and how many. I tend to be optimistic how much I can get. This was a project led from my cognitive scientists in Italy. I'm pretty sure, at least their research show that basically your kinesthesia, your perception, or proprioception is calibrated by your vision. Not all the time, but the reason I know that my hand is out there is I've seen it there. Sometimes it kind of calibrates and recalibrates. And this is then a problem if you can't see. So they wanted to replace the visual feedback with 3D audio. So they had a little device that made sounds that you could put on the arm and then get the spatial information through your hearing instead of your vision. And of course, if you're working with sounds, you want to look at, well, what do people like to have? And I think that was, in that case, we worked with, had a short questionnaire before, and then it's kind of a person, it was kind of an advantage working with kids who are visually impaired, that you could have a hand raising exercise and they wouldn't see the other guys raising their hands. So it was, I mean, typically otherwise when you do hand raising, it's a problem because everybody can see the hands going up. It's, oh, everybody's raising their hands up as well. And then we also had, part of this workshop was just to design something, a cool combination of a material and sound. And in this case, we had little NFC tags. So you could play the sound by putting the NFC tag on the phone. And then you put the NFC tag on the material and you got this combination of sound and material. And added to that, actually, was we had the opportunity to do like a sound story workshop at summer camp with visually impaired kids. And I think what came out of that was, I think that is sort of well known, but you can't just go for pleasant. The annoying sounds are also really important sometimes. You want to have the explosions or maybe the mosquitoes or whatever. And it was also interesting because for the touch preferences, the blind kids had, there were some materials that, at least for me, was a little bit of a surprise. It's like this kind of soft, rubbery materials like that often exist as play materials, like clay and soft rubber. Lots of toys are soft rubber, were deemed very unpleasant. So preferred hard materials. So we also did workshops with the kids once we'd had more sounds and asked them to create games. And this was, they had this little matchbox thing on the arm, and it would play a sound when the arm was moved, it would be quiet when the arm wasn't moving. So it was really basically just sound on and off, but located on your arm. And you can play quite nice games for this. So these were two kids who had never been able to play that kind of game, catch before. It was interesting because we had also thought that, oh yes, it's a sound that matters. We had got several like sneaking games where you try to silent, sneak past. So you can get fairly, I thought that was kind of an interesting reminder that you can have very simple tech and you can get pretty advanced socially games. So in this part, or in this project, I think the important things for us was doing workshops with the kids. And this was always a challenge because we did all this in Italy. So we always had to have a translating person or several persons translating for us because none of us spoke Italian. And then trying to do co-design. And well, yeah, there is this thing about adapting standard methods to non-visual use, which generally worked well. I have this embarrassing failure report, which I learned from, so I think it's okay. But anyway, since you had this little thing, potentially you could do gestures on it to interact with it. Maybe you do settings or something, change sound. So we had one workshop with the kids where we wanted them to come up with gestures. Thinking that yes, of course you could always illustrate a gesture. One of the things that we hadn't thought about, which is very embarrassing, is that they couldn't see the gestures the other guys were doing, which would be a nice thing at a workshop. So we managed to deal with it because we went around and showed the gestures to them. But that is something. The next time I do this, I will think about that better beforehand. This moving to yet another. I'll just check the time also. After that, we've had a couple of projects with rehabilitation. This is after stroke, preventing secondary stroke. So in this case, we're not typically dealing with users who are visually impaired. So we have used slightly more visual design tools. And one of the things in this activables, the idea was to do some kind of tangible thing that would encourage physical rehab exercises. And of course, if you talk to interaction designers and you say the word tangibles, everybody knows it's tangibles. If you talk to users, typically they will not know what tangibles are at all. So we were doing these video tools, which turned out, video prototypes, which turned out to be really useful. And of course, it's easy to fake stuff on video, so you can really illustrate how things are supposed to work. And also another thing that idea, which actually I got from a workshop at Mobile Chair, I think it was, this using magic, because one of the things that tends to happen when you work with users, also if you ask for ideas, it's not uncommon to get the response, well, I don't know anything about tech. No idea. And try to work around that hurdle. You could say, well, assume the thing works by magic. So, the magic, of course, we had some restrictions that, because this was also about stroke, it was a new project. That the magic can't make you magically well, or remove your aphasia or something like that. But the magic runs the tech, and that was the thing. And to support this workshop, we did it in, I think it was with the Stroke Association here in the UK. We had some idea cards to sort of explain what we were after, but also some physical props. So you could hold up a pair of glasses, for example, and explain what we have. So bracelet, a sew, for example. And then we split people into groups and basically have this kind of design workshop. And my impression was that this worked really well. I remember the guys in my group, because I was seeing one of the pictures there. Before going into the group, I don't explain much. I'm very bad with coming up with ideas, and we had lots of ideas. So I think if it was the magic or the combination of magic or the idea of magic and all these things, really worked very well. The one group we had some difficulty with was the group with aphasia. Still worked, but there are problems when just it takes longer when you have language difficulties in the group. So it's something to think about. In this case, it kind of worked itself out because we had one group with aphasia and they could be on the same level in a sense. I've had that problem in other workshops where you have maybe one person with aphasia and the others don't, and it's really difficult to let that person. It's very easy that they kind of don't get to participate, or that they kind of get out. So again, of course, in any project you'll be building and testing, and it's so interesting if you see the top one there, because we had focused on doing kind of balance mat. Yeah. And that person who is down, so you think, oh yes, balance mat, you stand on it. And of course, the first thing the physiotherapist did was down and trying to do things with our hands. You learn a lot about these things. So from that project, let's say testing in the home was really important. Basically, it's these things that trip you up. Because we had kind of a system where you had a balance mat, you had a tablet, and you had kind of a light tree that lit up as you did your exercises, and the lights were too strong. We had done them in the lab, and the lab has these really strong lights, so you think, yes, this is good, and then you bring the tree into the home environment, and the whole room turns green, and that's not very nice. So we had to damp down that. And again, because we had all these different parts with different speakers in our first prototype, there were several things that needed charging. And if you leave this in the home of a person that might have memory issues, it's not really a good thing, because yes, what will happen is that they, maybe they forgot the charging, and then when they're going to try it, it doesn't work. And also handling, actually, that was a commercial tablet, and our application was made with big signs, and it was kind of generic, deemed easy to use. But sometimes you needed to interact with the tablet itself, and that was an Android tablet, and tiny little things that you have to do. So it feels like you do a research project, you have all these cool things, and then it's fairly easy things like charging. Tricks you. Sorry. So in this project, important ones were like video workshops and interviews, testing in the home, and working with both stroke survivors and professionals. And actually this thing with complexity, having several different things when you do a prototype and charging. Of course, relying on consumer products. And I'm thinking, since I'm almost out of time, I'm going to skip some of the others. They're more AR oriented ones, so maybe not so much haptic, although it's always the haptic interaction. If you call your kinesthesia or your proprioception part of your haptic sense, which I tend to do. So I'm going to skip this. It's optimistic about things that you can cram into lines. So I have a few final slides. So I think this is slowly going away, but it's still sometimes there. This is an old idea that you have science that finds the stuff, industry applies, and conforms, and it turns out that doesn't work very well. And I think these days most people are aware of this, although sometimes you still feel this. And when you're working with design, it's also like there is this thing about who are you doing it for a single person, or are you doing it for a wide range of persons, and how do you deal with that? A note that it's not just the system, it's all the things around the system. If you're talking buildings, for example, is this parking, access, transportation that you need to think about? For example, when you do workshops. But if it's ICT, sorry. Okay, which is very common. If you have a really, really good app and you can come into it or access it, you will have a problem. So I'd say, sorry, I think I said this already at the start, but that there is nothing per se that prevents the involvement of persons with different abilities in incorporating design activities. I mean, the challenge really lies in making good activities and finding good materials to work with. And of course, the good things with doing co-design is that I think for me, the main thing is that you open up for the unexpected. If you're only the design team, only you sort of, you go on your own ideas and you never get these surprises, these unexpected insights that will maybe lead you in a new direction. So it does encourage thinking out of the box. And with workshops, I mean, you learn, you get some creative input, maybe, but you also learn a lot about the particular situation. So, I mean, it's not always the designs you do in a co-creative workshop will be the ones that you use, but they will be some sort of inspiration. But certainly, you'll gain an improved understanding of the usage and the context of use. So I'll just see what the next one, because I think I had some added, that's practicality. So I think if this is sort of where I should stop, I will stop that. And if there are any questions.
Thank you, Sriram, for a really nice talk. It makes me really appreciate how hard it is to design something useful. My question has to do with design for one versus design for all. So Charlotte presented a paper yesterday. I was a co-author about designing speech delivery and aids for the individual. So this is a Google employee, and Google has this notion that we design for one, and then eventually we'll learn how to design for all. So the idea is that, when you think about deafness, everybody is deaf in somewhat different ways. So if we set out to collect lots of ideas, try to solve everybody's problems, it may not work out that well. So let's look at Dimitri's specific difficulty. Let's help him with the confusions, the biasing group he has, and let's see how that works for him. And then try to learn from other individuals. I just wonder what you think, it seems like two very different approaches.
I think you can do both, depending on, we certainly have a lot of projects where we start almost with one user. I had a colleague, this was years ago, who did something for very severe brain injury, for example. And I think for Gerd, he was designing for she could move her eyebrow a little bit. That was it. And the final concept he came up with then could worked for a wider group of persons with severe, so similar, or not similar problems, but severe interaction problems. So I think that that's one approach, but I also think that in some cases you can get multiple inputs. But I must admit, since we're working with persons with disabilities a lot, when we do a workshop with more than one person, they're not very many. It's even when you work with blind people, they're not that many around. So we won't have this huge amounts of people. Well, I think what we tend to do, what we should strive for, is to get spread. If you're thinking design for all, that you maybe have one with problems, and then you have one with motor problems, and then you have, so you kind of get this spread. So at least you try to widen your vision or your inputs or what you want.
Questions? In this big act, what was the aim?
Yeah, that it was sensory stimulation, basically. So you interact. I should maybe say that that project, these New Zealand environments, that they're not interactive, typically. You have a lot of light flipping, you can have sounds, but they don't react to what the person does typically. And that was part of that project, was actually to do something that, you know, responded to the person. So in this case, it was something that responded to your HAID and maybe encouraged activity or some kind of movement.
So was it to help activity for those disabled children to interact with the environment, whether it's to learn from that?
Yeah, you just have, I think these are kind of creating experiences. And it is, I mean, having positive experiences is beneficial. So it's not like assistive device. It's now you're talking to someone who isn't expert on sensory stimulation environments, but I think it's considered a positive thing generally, just to have this kind of stimulation, and you feel better and maybe function better as well.
Thanks, Charlotte, for sharing that fascinating project. I wanted to go back to something you said earlier on about the sort of inherent power imbalance between sort of the researcher and the participant. Have you come across any effective strategies for addressing that? So was it really just about people skills, building relationships, spending time?
I think so. You try, I mean, there are all these tips that you say, oh, we're not testing you or whatever, and you are the experts. But of course, one thing that you actually can do, which is sometimes difficult in research projects, is you know, showing people that they're valuable by paying.
Yes.
Because often in projects, yes, the researchers get paid, and you know, everybody else gets paid, but the participant don't. And of course, there are reasons, because the ethical committees don't want us to pay people. So it's, but.
That's a good point, I guess, factoring that into any sort of
So, but I think it's a lot about, yeah, great people skills.
Last question, please. Thank you so much for the talk. And I wanted to ask you something about, like, in a future where AI might be a solution to adaptation for the users, of course. Does this change in some kind of way the way we design, like the way we, for example, create workshops and the way we do participatory design, with the idea that we might have a tool that adapt to people? So we, instead of, like, in some sort of sense, instead of designing for a single solution, we design for some sort of broader idea of the solution. Does this change the way we approach them design and the way we design things?
Yeah, I wouldn't say that it should, because you still need to design how the AI is supposed to adapt. Actually, I think it's sort of interesting you say AI, because I'm sort of a little bit in touch with the AI groups, at least in university, and it feels like at least that AI crowd just disregard everything we know about usability and the process and everything, and then they just do the AI systems. So it's, I'm hoping that, you know, what we actually know about how to work with design will penetrate into the AI crowd at some point in time. But yes, of course, the details of how you do it, I think, will change because you have to think about how do I design a good workshop around this, or how do I design my materials? But the way, the overall way of working, I still think.
So let's thank again Charlotte. Thank you very much.
Yes. Talking about mapping monophonic MIDI tracks to vibrotactile stimuli using tactile.
Good afternoon, everyone. My name is Sriram Subramanian, and I'm going to present the project Mapping Monophonic MIDI Tracks to Vibrotactile Stimuli using Tactile Illusions. Okay, so experiencing music is a complex, multisensory and cognitive process. In fact, musical sound produces vibrations that may reach our sense of touch. Researchers have found that some musical features can be converted to vibrotactile stimuli. Here we can see just two examples. The one in figure A is the frequency model, which is basically sending different frequency bands extracted from an audio file to different actuators and located in different parts of the body. It was developed by Karam et al. In 2008. And almost at the same time, the same Karam et al. Developed the track model, which is similar, but we have a multi-track session there with different instruments, and the instruments are sent to different actuators in different parts of the body. And basically, over the last decade, these models have been explored and optimized, and we have summarized systematically all of them in a musical haptics review just published last year. What is the problem we usually find here is that there is a common limitation. The frequency range of perception of the sense of touch is from about 3 Hz to 1000 Hz. And as you may know, the auditory range is from 20 to 20,000. So the information embedded in higher frequencies is usually lost. And also, we don't really know what is the actual emotional response to vibrotactile stimuli that comes from musical composition. To help overcome these limitations, we explore a resource known as tactile illusions. A tactile illusion may be defined as the discrepancy between a tactile stimulus and what is perceived. We can see here in this example, two real stimulus from two actuators and a phantom stimuli or an illusory actuator that is perceived in a different location in between both actuators. What we propose is to use tactile illusions to convey more meaningful vibrotactile stimuli. In our proposed algorithm, audio was played back from monophonic MIDI files to avoid overlapping notes. So each tactile illusion corresponds to one note only. As we can see here in the figure, extracted from Audacity, in the lower channel, we can see in yellow a MIDI event, and in the upper channel, which is a stereo channel, we can see the signal corresponding to a tactile illusion, which in this case is a phantom motion. From the MIDI file, we extract some musical information, and we create a vector in the auditory domain. As we can see there, there is a vector with the note played or the pitch, the frequency, the onset time, and the duration of that note. The tactile illusions we are going to use, or we are using in this application, are phantom motion and funneling. Phantom motion is basically a sensation of continuous movement created from one actuator to the other, while funneling is an illusion of an illusory actuator located in a specific location in between the actuators, the real actuators. As we can see here, one is on the left from the center on the left and from the center on the right. Besides the versatility of tactile illusions, we try to associate the apparent movement with the performance of the musician when playing. For instance, here we have a violin bowing, and the movement of the apparent motion for the apparent movement is related to that. And with funneling, we create an illusion of notes played in different locations between the actuators. Regarding the technical and psychophysical implications, we have our own actuators that we built. We can see there our actuators located in the forearm, which have a satisfactory response from 90 Hz and above. And therefore, we have an effective range of frequencies between 90 and 1000 Hz. What we do first in our auditory tactile mapping is to extract the frequencies, the maximum frequency and the minimum frequency, and if they are not in between the effective range, we just transpose it. But what we do is to transpose one semitone the whole composition. So it causes that when we transpose and the frequencies are out of the range, the MIDI file is rejected. So we take the musical information and we render the tactile illusions according to what can be seen here. We get the number of tactile illusions, the type of tactile illusion, the frequency, the onset time, and the duration. And depending on the duration, we can see that we generate phantom motion and funneling. Another feature of tactile illusions is the spatial feature, which in the phantom motion is the direction of movement. So here, if we have a spatial feature of the previous tactile illusion, that is phantom motion from left to right, then the next tactile illusion is going to be from right to left, and vice versa. Then if we have funneling as the previous tactile illusion on the left, the next one, if it is funneling, is assigned to the right, and vice versa. If we have that the previous tactile illusion is phantom motion from left to right, then, and the following is a funneling, it is assigned to the left, and vice versa. And finally, if we have that the previous tactile illusion is funneling on the left, and the next one has to be phantom motion, it is assigned from left to right, and vice versa. Finally, when we apply the algorithm, we have two new features in the vector, which is a vector in the tactile domain. We have the type of tactile illusion and the spatial feature. We perform an experimental evaluation. Our experiments were randomized, blind, and controlled. So the participants went through a practice session first, and then they were randomly assigned, half of them to experiment A and the rest to experiment B. The participants were 20, half of them were male, half female, between 19 and 52 years old. We also gather some information about musicians, as you can see there in the table. The practice session was to familiarize the participants with tactile illusions, as these are a kind of novel stimuli that they are going to feel, so they need to understand and to recognize the tactile illusions so that they are able to evaluate the arrangement of tactile illusions. The Vibrotactile interface has these components, basic components, a computer with audio signal processing, DAQ, high fidelity audio signal amplifier, and a pair of voice coil actuators. These are our voice coil actuators, which are made out of neodymium 10 millimeter diameter, 10 millimeter HAID magnet, and the enclosure is 3D printed. The stimuli for the practice session we can see here in figure A is an example of the phantom motion, the signal rendered from MATLAB, but we are visualizing in Audacity. And in figure B, we can see the funneling, which are signals for illusory actuators, each of them moving, jumping from one actuator to the other, so that the participant can recognize them. The participants were seated in a chair, they used earmuffs, closed their eyes, and then evaluated the level of clarity of the illusions. And here we can see that all of them practically were able to recognize the tactile illusions at least as slightly clear. We had 2 phantom motions with 2 durations and funneling. For the experimental session A, we wanted to know if adding the tactile modality to the auditory had any effect on the emotional response. We added audio interface to have two outputs for stereo headphones. And we used the fourth movement of Summer by Vivaldi, played by a violin. Here we can see the lower channel, the MIDI file, and the upper one, the arrangement of tactile illusions. It was just 11 seconds, of course. They evaluated the emotional response, and they also reported the recognition of musical features in different scales, as we can see there. In the experimental session B, we did the same, but without auditory feedback. We wanted to know what happened with the tactile, with the arrangement of tactile illusions alone. And here we have the results. When comparing the auditory with the auditory tactile conditions, we have that the auditory tactile condition was just happier than the auditory. And there was no significant effect on the other emotions, as well as in valence and arousal. Comparing the auditory and tactile, we can see that there is a quite significant effect. It was felt happier and more peaceful, less sad and less scary, and the valence and arousal was also increased. Regarding auditory, tactile, and tactile, we can see that the tactile condition was just happier, with no effect on the other emotions, as well as in valence and arousal. And here we can see the relation of increase in valence and arousal. We see that the relation is, adding the tactile condition to the auditory condition to the musical excerpt increases the valence and arousal almost linearly. However, we believe that we need more participants and more experimentation to support our suggestions. And here we can see the recognition of musical features. We can see that in the auditory, tactile, and the tactile conditions, rhythm, tempo, and melody were very good recognized. And genre was the less recognized feature in the 3 conditions. Finally, we have proposed an algorithm to map monophonic MIDI files to arrangements of tactile illusions. Our results support our suggestion that tactile illusions can be used to add dynamics to arrangement of vibrotactile stimuli, and we support this with our results of increasing arousal. And although it was not possible to assign a specific emotion to any condition, we found a significant effect of adding the tactile modality in the form of tactile illusions to to the auditory condition. The arrangement of tactile illusions conveyed rhythm, tempo, and melody to most of the participants. And we just finished exploring the emotional response to arrangements of tactile illusions rendered from musical excerpts with confirmed emotional labels, happy, sad, scary, and peaceful, as it was done in Bielar et al. 2008. We got some results that are going to be published shortly as a master thesis in the repository of the University of Oslo, and the results are supporting our suggestions, actually. In future work, we hope to find an algorithm that combines various resources to properly translate music to vibrotactile stimuli. Here we can see the references we used in this presentation, and thank you so much. We are always open to collaborate.
Really nice talk. I was very pleasantly surprised that the movement actually led to a strong emotional response. So I'm curious, have you tried the sensory saltation as well? So in movement illusion, Dr. Jones actually has a review paper, at least funneling apparent motion, and then there's saltatory motion. So the difference is that instead of feeling a smooth movement between the two, you feel like there's something that running. I just wonder if that's you're even more interested in the life, or just wonder if you have tried that.
Well, yeah, we are now optimizing our algorithm. This is a quite old algorithm. Then we have a new one where we are actually implementing that. We are trying to find what happens when there is this transition from generating funneling, a lot of funnelings, and then getting this transition to more iterative sounds, and then a continuous movement. So we have the algorithm, we have not tested it yet, but hopefully in the future we are going to try to get if the emotional response changes. The emotional response is different from that of the auditor, the musical excerpt, because we cannot get negative emotions. It's very difficult. We can increase arousal, valence, and make it more interesting and happier, but we cannot get it sad or scary. It's very difficult. We don't know yet how to make it, but probably in the future. Thank you.
Another question. Hi. I wanted to ask you, do you think your results and what you're trying to do with funneling, etc., can be a way to prove but support embodied cognition theories? I mean, since for motion, of course, and the relationship between motion and audio, basically.
Good question. Well, we don't really know, but as we are trying to build it up from bottom to top, we are now trying to create not sonic events, but vibrotactile events. So we think that we are gonna build up this embodied, like a new kind of vibrotactile experience, hopefully musical experience, because we cannot say right now that we actually have vibrotactile music, because music is a whole experience, and we cannot get that experience just with the vibrotactile feedback. So we are not sure about that, but probably we have to test it and find out if we can relate it with embodied cognition. Yeah. Thank you.
Last question, super cool, first of all. I was just wondering, so you tested the music with the tactile illusions against just the music alone. I was wondering if you considered also testing with tactile or without any kind of illusions, like if there was a way of just doing it against some kind of.
Yeah, that's a very good question. Yeah, that's a good question, because we considered testing just the audio signal sent as it is to the actuators, to make them vibrate without any synthesizing or tactile illusion rendering. But we found that there are some researchers that already have some results, and we wanted actually to compare our results with them, with the results they have. And we are getting exactly the same. There are some papers that they say that the negative emotions are very difficult to convey. And we had these last experiments in the University of Oslo, where we had about 50 participants, and the results are the same. So for us, was very interesting to test the tactile illusions, the arrangement of tactile illusions. But in the future, for sure, we have to compare with the actual vibration of the musical excerpt alone, or with some signal processing, probably. But yeah, that's a very good suggestion. Thank you.
Thank you. We can upload the speaker again.
Thank you.
Papetti, who will talk about the accuracy of musical pitch control through finger pushing and pulling.
So, good afternoon. Yeah, my name is Sriram Subramanian, and I'm going to present our research titled Accuracy of Musical Pitch Control through Finger Pushing and Pulling. First of all, a little bit of context. We've been doing research in the context of musical haptics for a few years already. And we can say that musical haptics is, on the one hand, concerned with the investigation of the role of haptic feedback in music performance, so from the musician's perspective, and music experience, so from the listener's perspective. And second, concerned with the design of haptic devices for musical interaction and enjoyment. So we are, for this particular research, we focused on pitch bending, which is a key control for musical expression and found on several musical instruments, such as string instruments or even percussion instruments, such as the tabla. And we noticed that with modern tactile digital musical interfaces, we can now achieve a rather natural direct interaction where we can modulate different parameters of the pitch in a very direct way. So, for instance, I'm playing a surface, whatever surface, it could be a touch screen, could be an advanced kind of keyboard. And I can bend, I can slide my finger to modulate or bend pitch. This is nice, so much closer to what happens with real musical instruments, traditional musical instruments. But that opens a major challenge because such devices don't offer haptic feedback. And so control accuracy is it's not that obvious. And so we set up an experiment where the task was to bend the pitch of a synthesizer until matching the reference tone. And this was achieved by either pushing forward, so to increase the pitch, or pulling backward to decrease the pitch. A finger on top of a haptic surface. And for that, we used a self-developed haptic device, which we call the Touchbox, which offers a touch panel, which is able to track 3D forces and provides vibrotactile feedback, which is driven by audio signals. And we stuck a little piece of sandpaper on top of the plexiglass panel to prevent fingers from slipping when pushing and pulling. We had 31 subjects, all of them were trained musicians. We had different target pitches randomized in a continuous range between A#3 and D4, which is a rather narrow pitch range, but I'm coming to that a bit later. So we were focusing on also on the range of maximum tactile sensitivity. The initial synth pitch could be between 1 and 3 semitones above or below the target pitch. For synth sound, we had which was provided through headphones. We had a very simple, very basic low pass sawtooth, so nothing too boring or nothing too complex. And we had 3 kinds of vibrotactile feedback: no vibration. Second was using the same sound, which was basically the synthesizer sound, which we refer to as pitched vibration. And we had noise. In this case, was white noise band passing the 40 to 360 hertz range. Vibration amplitude was normalized in order to be clearly perceivable. And we measured pitch accuracy, of course, that was the main goal. So we had a performance assessment, so something that is objective. And we measured error in cents, where a cent is 100th of a semitone. And we also had a subjective assessment, where we asked participants to rate the perceived agency. So like, I feel I'm in control of this instrument, and the confidence of correctness, or I feel that I gave the correct response, and the pleasantness of the experience. So if they felt the task was pleasant to them. And ratings were given in a range, in a continuous range between 0 and 1 by using the visual analog slide. So coming to the results, here are the raw data. Pitch accuracy, as you can see, was mostly influenced by the different gestures. So we have pull and push, left and right. And pull was characterized by general overshooting and push by a general undershooting. And we fit a statistical model to analyze the significance of such effect. And we found that, again, only gesture had a significant effect on error, whereas the effect of vibrotactile feedback was not significant. And we also investigated the significance of the difference between the 2 gestures, finding that in that case the estimate was a bit higher for push, but with a slightly less than 95% probability of a non-zero effect. And also we found a rather clear learn effect throughout the sessions. So subjects started with a rather high error, so they perform worse at the beginning, and they became better and better throughout the session. And this is especially visible for push. You see the dashed lines here, and somehow the 2 gestures converge towards the end of the sessions. Here are the raw data. Again, can be seen that for the pull gesture, so the red bars here, pitch vibration had a positive effect on all 3 attributes. So you can see the pitch vibration is always the 3rd one for each attribute. So it's a bit, so the effect is not big, but it's there. And for that, again, we used statistical analysis, and we found that actually push has a credibly positive effect on the attributes, and noise had a credibly negative effect. We couldn't really investigate the interaction between different factors, so like if we consider pitch and the pull gesture together, because of not enough data available. But summarizing the effects, we can say that well, errors in general were in line with those of auditory pitch discrimination for young normal hearing adults. But of course, we cannot really directly compare passive task like that of auditory pitch discrimination with performing pitch bending. But it was nice to see that this was comparable. So, and even if it's a slightly less accurate push required less time and gave better overall ratings. And so somehow we can consider that since the two gestures at the end somehow converge in terms of errors, push may be regarded as more efficient for repeated tasks, whereas pull can be considered more suited to new and rare tasks. Concerning vibration, we found that in general, pitch vibration gave slightly lower errors, and noise vibration gave slightly higher errors. And but as I mentioned before, there was no significant effect on pitch accuracy, and for that we need a larger scale experiment. And we found a slight effect on subjective experience. So this is somehow like a recurring issue we found in our research. We somehow persevere in targeting musicians, but maybe that's not the right way, because professional or very well-trained musicians are probably so good in their motor control skills that they probably would, so that they can really perform very well only based on their auditory perception, and sometimes even without, just based on their motor memories, things like that. And so the question is, did these subjects perform the task just based on what they heard? And so in the future, we would like to target early stage learners, children, persons with impaired pitch discrimination, because it is known that multisensory enhancement is strongest in conditions where sensory information is really effective. So in that case, adding vibration should be more beneficial. And but still, even when targeting musicians, maybe there are scenarios where vibration could be effective, and that could be in ensemble playing, so where when musicians cannot really hear what they are playing clearly in an orchestra, for instance, or for DJs or electronic computer musicians working in the club or noisy environments. So in that case, vibration can be not only affecting the, let's say, the experience, the subjective experience, but also their performance. And this is something that we would like to investigate in future research. So that was it. Thank you very much.
We have much time for questions. Feel free. I have some questions. You showed us a figure where the performances were converging between push and pull, and I have the impression that the only thing that prevents them from conversion is that you don't have that many trials. Yeah. Can you imagine that with 100 trials, they will eventually meet, and so, or any reason to think that the push will always overestimate it?
Probably it's going to be very, very marginal at the end. And what's interesting, I think, is the different gestures. So what we I forgot to mention that when we consider standard digital musical devices like a MIDI keyboard, we normally had like a spring-loaded lever, for instance, for performing pitch bending or a wheel. And yeah, so our interest wasn't really just on testing vibration, but also to test different gestures. So it's still something open, I think. So there's no given standardized way to map pitch bending nowadays with touch screens. So basically, I think it was interesting also to test, or just focusing on push and pull as to gestures. Yeah, and yeah, it feels probably best when you push in general. So it's more natural somehow experience. Pull feels a bit different, but yeah, something more interaction design oriented. More questions.
So I may have one more. As I understand, they were just pushing or pulling, but doing nothing else with the other hand. I wonder what all this becomes in a playing context where they're just playing with the right hand, for example, and trying to express themselves with the new pitch bend.
Yeah, the idea is that with the same hand that you're using to play, playing notes. Playing notes and also bend pitch at the same time with the same fingers. That's the idea. So same finger, yeah. Or something that you can do with current interfaces, such the roll symbol, for instance, touch screens. So that was the idea.
Yeah. And were you sure that everyone had like no motor sensory limitation?
Well, we asked them.
Okay.
And there were all musicians.
All musicians.
String players and some young players.
There are no other questions. Thank you. Welcome the last speaker of this session, who is Baptiste Roux-Lacan, and he is going to speak about the perception of guitar strings on a flat Visuo-Haptic display.
No, but it was.
So, good afternoon, everyone. I'm Baptiste Roux-Lacan from Sorbonne University in France. And I'm currently a first year in a PhD in the Haptic field. And very happy to be here today to present the results of our research, which deal with the perception of a guitar string on a flat Visuo-Haptic display. So this project takes place during a 6 month internship. 6 month internship that collaboration between ISIR and D'Alembert Laboratory, both at Sorbonne University. So a little bit of context. As you've seen during these 2 days of the conferences, the field of musical instrument become more and more digitalized, and they create a new kind of instrument, create the DMI for digital musical instrument. This kind of instrument bring new possibilities, such as, for example, overcome the physical limitation and doing stuff that are not possible with the physical counterpart. However, this kind of instrument suffers greatly from a large drawback, which is the absence of feedbacks. And this absence of feedbacks prevent the musician to actually feel his instruments, and it diminishes its ability to play, and also the listener's quality of listening. We notice that there is recently an enthusiasm toward this type of instruments. Many studies have shown that adding haptic feedbacks, the addition of haptic feedbacks can improve the quality of playing the musical instruments. They are useful to improve this quality, but also it increases the pace of learning and the pleasure of practice. So this is in context that we wonder how different types of haptic rendering on the DG and the guitar string, rendering which are coupled with multisensory rendering, are fed by user. And for that, we decided to investigate 2 questions. And the first one is, does the recording location influence the user's ability to discriminate a virtual string, and if and what will be the level of raise perceived by the user for these different signals? So for that, we firstly investigate. We firstly implement haptic and visual feedbacks in order to perform a user study. So to begin with, let's see what type of measurement were performed. So in order to perform a user test where people need to discriminate 3 types of notes, we recorded 3 different notes corresponding to 3 open strings. So the high one at the note E4, the middle one at note G3, and the low one at note A2. These 3 notes are very close to each other, allowing challenging tests, but are spaced enough to be above the chancellor. In addition to these 3 notes, we recorded 3 different positions. The aim of this recording position was to test if the signal component generated during the movement or during the interaction between the sensor and the net impacts the discrimination capacity of the users. That's why we had 3 different positions. The first one was placed on the tips of the right-hand index, where so it corresponds to action hand, where it performs the movement of blocking the string. The second one was placed on the tip of the left-hand finger, and in this case, the finger pushes the string at the level of the guitar fingerboard and stay motionless. It's a more passive way, we receive the vibration of the string. And finally, the last one was placed directly on the guitar fingerboard fret, and it's a record more natural from what people will get. After measure this different signal, we also perform a spectral analysis in order to see what kind of vibration and frequency are transmitted from the string to the sensor. So we start surprise in the last two measurements we have the initial frequency and its harmonic. But what is more interesting is that for the first one, so the right hand, in addition to the frequency corresponding to the movement at a low frequency, we have also the initial frequency and the harmonics. That means that the frequency are transmitted from the string to the finger, even if the string vibrates only during the moment where it splits under the finger during the movement. So, so for concerning the haptic feedback, we decided to choose these three feedbacks, so right hand, left hand, and fingerboard. And we also add two additional feedbacks corresponding to the right hand. So the two one with high pass frequency at 70 Hz and the low with the low pass filter. So high pass filter and low pass filter both at 70 Hz. So we chose this frequency to presently activate the tactile channels, so respectively related to the FA1 and FA2 tactile afferents, with the aim to investigate whether different low frequency tactile nodes or high frequency peak will impact perception. So in addition to the haptic feedback, we also implement a visual feedback. So it based on the equation of resulting strings at both ends, which allow us to control the different pressure. We implement the theoretical three frequency that we measured previously, and also we only implement one mode due to technical limitation. You can see the screen like that. So we perform the user study. In our user study, participants had to recognize three types of notes, thanks to the haptic and visual feedbacks, and that for each 5 type of feedbacks. One type of feedbacks is called an experimental blocks, and it's composed of 30 trials, so 10 per notes, and 3 and 6 additional training trials. A training trial is allow the user to get used to the Visuo-Haptic feedbacks that they will encounter during the block. So in this test, the user had to place his non-dominant hand on the actuator, placed at the top of the screen, the Vibrotactile actuator. And with their dominant hand, they will plug the virtual screen, and after release it, he will get the haptic and visual feedbacks. After releasing the screen and get back the feedbacks, another screen will appear that asks the participant which note was played, a high one, a medium one, or a low one. They choose one of them by pressing the corresponding button. And finally, after the 33 hours, participants were asked to rate the realism of the feedbacks that I just played comparison with what they will felt with real guitar. They choose by with thanks to a score bar between 0 and 100%. So our study took place in an isolated space, and participants wore noise cancelling headphone and earplug to avoid auditory issue. It lasted between 25 and 30 minutes. In total, 21 participants took part of the experiment. And we also asked before the experiment to the user their level of musical knowledge, and between 0 and 7. 0, there are no conditions of knowledge of music, and 7, they are quite professional. And also if they are used to play the guitar. So for the different results, first of all, despite the fact that there are different some trials are randomized, we still have a slight effects that take place through the experiment, supported by a Pearson correlation. This correlation may be due to first to the discovery of the experiment, which may have require some time to master. However, it's quite surprising that this performance at recognizing the note continue to improve through the experiment. And we also performed confusion matrix. So we compare the answer obtained to the expected one, and we notice that there are a confusion between the high notes and the medium notes. The high notes and the medium notes. So approximately 30% of confusion, which is quite surprising because we proved first that this confusion will more happen between the low one and the medium one, which are closer in terms of frequency. And also, we notice that the feedbacks related to the right hand are seems to be less well perceived to the other two. And this is confirmed thanks to an ANOVA that we performed. So first of all, thanks to this, this ANOVA tend to show that the type of feedback have an effect on the discrimination capacity. And without surprise, it tend to show also that the feedbacks linked to the motionless and or motionless record tend to be better perceived than the other three. However, we can still underline that despite the fact that the results are very low, the three feedbacks linked to the right hand are still above the chance level, which is approximately at 33%. And that means that the user keep a certain capacity to discriminate Visuo-Haptic feedbacks, even if the recording is noisy or part of the frequency is filtering. And concerning the perceived realism, we performed another ANOVA that tend also to show that the type of feedbacks have an impact on the perceived on the quality of the rating. Also, like the previous study, we noticed that without movement, the record without movement are much perceived, much more appreciated than the other three. And on the second hand, on the second graph, you can see that the string vibration recorded directly on the guitar neck, so on the fingerboard, and without the finger in the recording loop, was the highest rated by almost everyone. So this result confirms that fingerboard haptic feedbacks is not only quantitatively preferred, but also this preference is done in a systematic way. So to conclude, we also perform statistical analysis on the musical knowledge and on the guitar playing experience, but both don't have an influence on the user's feeling capacity. That may be due to the fact that our devices is too different than what they feel with a real guitar. So we also notice that the recognition of the digital guitar string vary greatly depending on the location where vibration were recorded. And the users tend to perform better and prefer when the haptic is not filtered by the finger, so directly on the guitar. And even in this case, even if the person doesn't have any knowledge of musical knowledge. Finally, the user still managed to recognize the different notes above chance level, even in the case of noisy haptic feedbacks recorded on the right hand. For the next step for this project, we tend to want to create a new devices in order to study if the experience of the immersion have an impact on the user performance. Thank you for.
Some questions? Who's got some questions? Not make me ask questions.
So you think you must to the vibrations real?
Yeah.
Or not real? Or near to the real?
Yeah, we ask them to wait between 0, it's completely different and nothing to link to the real guitar, and 100% is like feel like playing.
Did they give any feedback about if it was not that real, was it perceived good or not or bad?
Yeah, because we tend but yeah, it's a good question. They feel good
or better than the actual vibration of it. Better than.
It's
not real, but it's better than.
No, we didn't ask that because it's quite difficult to, if it's not real, to compare to a real what can be better than the vibration of the real instruments that we tend to reproduce. It's quite difficult to have them, even more if they have musical knowledge. Guitar,
Other questions? I have one thinking about realism. If I understand well, I'm right-handed, so what I had to do is to pull the string with my right hand and to feel vibrations with my left hand, always. Yeah. That's so. So people were exposed to vibrations on the left hand, but the vibrations could be recorded on the right finger or left finger or on the soundboard or fingerboard. Is that so? Yeah. Okay. It's being a guitar player, I can't imagine feeling vibrations of my right hand into my left hand. It's quite strange.
The interest of the right hand was to see if it's the hand that injects the movement, injects the energy to make the string vibrate. And we wanted to see that we feel more the energy of just the vibration of the string that we get the left hand. But in this project, the vibration was quite limited to the one finger. So that's why we want to make another study after that to improve to make a larger zone, for example, on the ball end or on the torso, on the torso. Sorry, I'm quite bad with English. Torso, because when guitar play with an instrument, it's tend to have a vibration on his whole body, not just in one place.
Yeah, but one more quick question. You recorded 3 notes, and were they open notes, open strings, or fretted strings?
Open strings.
So the picture showed a finger actually that pushed the strings.
Yeah, it's not push the strings, just place on the strings, not it doesn't push it. So
the left hand didn't move during all. So thank you. If there are no further questions, we can thank Baptiste again and close the session. Thank all. Stop sharing.
So it's a third keynote of our workshop. Thank you to those who are staying, and there will be a coffee break and one more session and drinks and tea. So stay as long as you can. And it is my pleasure to introduce you Professor Sriram Subramanian, who is the chair of immersive technologies funded by Royal Academy of Engineering, but also professor at UCL, University College London, our neighbor. Previously, before UCL, Professor Subramanian was an academic at University of Sussex and University of Bristol. He is also one of the co-founders of a company we know well, Ultra-Haptics, which is now Ultraleap. And Professor Subramanian's research is on developing new technologies for multi-sensory interaction. So today we are going to see different types of acoustic, levitation, and holograms technologies used for haptics and audio. Thank you very much.
Thank you so much for the introduction. So I'm really pleased to be here to talk to you about my work. So let me start with this one. Right. So this is quite an interesting picture, right? So the Academy of Motion Pictures have been giving out Oscars for a long time, and it's not just about videos. They also give Oscars for sound design, sound or audio quality, and sound structure and everything, right? So there are many Oscars that go out for sound production as well. And it's very interesting to note that there's nothing for the sense of touch or haptics. What we need to do to change that at some point in the future might be interesting to think about. But the world that we are embracing actively with metaverse and virtual reality and everything is actually going in the opposite direction of everything this community stands for: haptics and touch and audio. Right? So it's fully immersive visuals, no contact. So would be quite exciting to see what role we can play in making sure that we have a much better sensory immersion in the new world that we're all embracing. So this is a video from, I guess, 2015 or 2016 from CNET, where they were talking about gesture controls in cars, as if gesture control is not enough in virtual reality. They wanted to have it in automotive, right? So this is a video that really caught my attention.
Gesturing at your car, even when it's not broken down. I'm Brian Cooley from CNET, in search of the next big thing. One of the most interesting trends I've seen lately at the Consumer Electronics Show in Las Vegas and the North American International Auto Show in Detroit is a wholesale move to at least trying gesture control in cars. Take BMW, for example. They're looking at a technology that would mount up in the headliner or by the sunroof and look down at your hand, being able to figure out where it is and what coarse gesture it's taking, like a rotating motion, for example, that could simulate or replace turning a volume knob or a fan control. Volkswagen's technology flips that idea on its head, puts the sensor down in the console behind the shifter looking up, and it can tell which way your hand's moving and whether it's flat or bladed, as well as picking up push gestures that would indicate a selection. More futuristically, Mercedes' F015 concept car sees a world where the immersive infotainment system for the passengers would be gesture controlled. And Audi, even a couple of years ago, was showing us a technology where they would turn the entire windshield into a 3-zone head-up display and use gesture control to kick and slide panels back and forth between.
So I'm going to stop it there. I mean, the point of that video was that a lot of automotive companies are interested in gesture control. And the idea that you can control the dashboard of the car while you're driving, presumably, without any haptic feedback or any sensation of what you're doing there, right? So all of this motivated part of the work that we were doing when we were in Bristol on creating mid-air tactile interface, right? The idea is that you have a device where you don't wear anything, but you can also get the sense of touch.
Whenever I'm working with my hands or doing something with my hands, I'm not just looking and thinking about hands, I'm also attending to sound. I mean, I can't get anything from my pocket because I can't feel it terribly well. You know, I can't do something, I can't see. Often if someone passes me a cup, I would grab it awkwardly because I don't have the feedback of something coming from the fingertips saying you've actually picked up the cup incorrectly or taken it incorrectly.
So the context for this video is, right, so Ian Waterman is, probably many of you are familiar with him. So when he was 19 years old, he fell ill and he lost all his sense of touch and he could not feel anything in his body. So he's explaining the challenges he has in picking up a coffee mug or a matchbox from his pocket. So it's so important to have this sense of touch. And I know I'm in a way it's preaching the choir here, so you all know important to touch. But as someone who didn't really come from the haptics world, it was quite interesting for me to appreciate how important the sense of touch is. And that's what drove me to create or look for ways in which we can create tactile sensations in midair. Right? So one of the powerful things about gestures is you don't need to touch anything, the interface comes to you, rather than you going and touching buttons and not turning things on. So we wanted to have that advantage of walk up and use. but at the same time have this feeling that you've touched something and you've interacted with the device. So we want to give that sense of touch back to the person. So this is quite an old video from almost a decade ago, where we were looking at using ultrasound transducers to create the sense of touch by constructive interference patterns. So we create these constructive interference patterns where we turn on these transducers at different time instances, and through that people can get the sensation of touching the device. And in fact, the great thing is, yeah, so that's there's a demo from Ultraleap here today, so I'm sure you've tried it. And your Tom Carter is explaining the technology and how it works. Maybe in the interest of time and the fact that you've seen the demo, I'm going to skip that. So yeah, so this is the device where you can have the sensation of touch, and you can buy this from many resellers today. So this is not what I really wanted to talk about in this talk. So what I want to talk about is something else, right? So here's a video that I found really interesting. So I'm going to play this and then I'll explain what it is. It's quite a funny video, and what would be amazing is to be able to give you the feeling of this video. Right? So you have some sensory immersion that's not just audio and visuals, but also haptics. So that's what. Well, I don't know where. Yeah, there you are. I cannot even recognize you now, but anyway. So there's Dario and Emma who did this. Integration of MIDI and haptics into movie experiences in 5 years ago, where actually the same video, they picked it up and then they, looking at the peaks where you have sensory excitement, they give you tactile sensations there. Right? So it was so much more powerful and evocative in doing it this way. And it was really fun for me to find this video again. And in fact, today you saw the demo of Touching the Story, where we try the same thing, but we give you much more feedback and control, right? So I'm sure you all tried the demo and enjoyed it. I don't need to explain to you what the demo works. But you can have different kinds of rotations, direction control, tapping, and so on. So lots of immersive experiences possible there. And SoftServe, one of our partners, is in fact looking to see how we can directly sense your biosignals, so if we know you're sweating or you're having some other heart rate increase, then we can try and see if we can use that to give back to you as a haptic sensation. So we have this mid-air haptic device, so you can feel it on it. This is work in progress, but an early version of this was presented last in Visuo-Haptics. And all of these things, what they're trying to do is try to capture the complexity of touch, right? So, but I feel like even we're only scratching the surface in this, right? So when we talk about touch, we have many fascinating components to it, right? There's a lot of things that I heard in all the presentations today, and also what we've tried, which are things like, how much pressure, what vibration frequency you need to have, is it a temperature, or do you want to have pain sensations and so on? So that's on a functional level, you can give all of these things, but you can also go one level higher, right? So you can talk about agency, and in fact, there were quite a few presentations where they were asking users whether their perceived agency increased or not. So that's another thing you can look at. You can look at attachment, engagement, arousal, trust, bonding, right? So all of those things are slightly further out from the basic functional aspects of touch, but also it's interesting to see if we can recreate those senses. And then on further away, right, there's this whole concept of social touch and affective touch and experiential touch. So again, it would be great if we can think about how to do haptic experiences and tactile experience sensations to create this complex touch, right? So here's a video that I found. So I should stop this because So this video is actually came out from Deutsche Welle. It's a German TV program just a few months ago, and I've edited this video just to give a small clip.
One of the most important moments in our lives. This baby cannot see further than 30 centimeters yet, and our sense of hearing does not fully develop until we are 4 weeks old. We first experience the world through touch. Above all, we are better able to convey love and compassion through touch than through words, facial expressions, or gestures. Touch creates a much deeper emotional connection. How has the fact that we now have to keep our distance affected us and our relationships?
Yeah, so I think this, I don't have an ability to produce this high quality video, but this one clearly shows you how important touch is, and we've missed it all, right? I mean, in the last 2.5 years, the inability to hug your loved ones and your family members who are far away highlighted how important touch is. And I think as a community, we only start to scratch the surface in terms of what we can do with touch. So this is a project where we tried a little bit to see if we can mediate emotions through the Visuo-Haptic device. So the idea here was not that we automatically create emotions, but if somebody designed an emotional haptic sensation to go with a particular image, would a third person who doesn't know that connection be able to feel it and experience it? So we know that the emotion is not arbitrary and it can actually be transferred between people. So one person can design a haptic emotional device and then another person can feel the same emotional response. So
touch is one of the most powerful forms of communication, and the way that we touch embraces and mediates every type of human emotion. Our research has shown that a gentle touch around the edge of the hand suggests negative emotions, while a touch around the index finger is positive. We have demonstrated that there is a non-arbitrary mapping between emotion and haptic stimulation, so we can now begin to enhance the way we express our feelings through technology.
So yeah, this is just a short video, but again, the idea is that we can in a non-arbitrary way map visual experiences and design emotional responses in a haptics system. Here's another one that we did. So here we were looking at agency, and we used
touchless interfaces allow users to view, control, and manipulate digital content without physically touching an interface. Today, touchless interfaces are being explored in a wide range of application scenarios, from medical surgery to car dashboard controllers. One aspect of touchless interaction that has not been explored to date is the sense of agency. The sense of agency refers to the subjective experience of voluntary control of actions in the external world. In human-computer interaction, the sense of agency can be defined as the feeling of, I am who is controlling this. In this paper, we investigated the sense of agency in touchless systems using the International Binding Paradigm. Previous studies have shown that perceived time of a voluntary action and its sensory outcomes are shifted towards each other, so that the interval between action and outcome is perceived as shorter than it actually is, leading to a perception of compression of time. If this perception of compression of time is higher, that means higher sense of agency. Participants judge their perception of time by reporting the position of a rotating dot around a clock. In a first experiment, we compared touchless systems, a click gesture with physical interactions, physical button press. And we compared two different types of sensory feedback, auditory feedback and visual feedback on screen. Then, in a second experiment, we added haptic feedback to the touchless input action and compared it with visual feedback, Vibrotactile through a wearable glove, and mid-air through ultrasound. Our results demonstrated that the click gesture input behaved as responsive as the physical action. Physical and gestural input action exhibited significantly more sense of agency when they are accompanied by audio feedback compared with the visual feedback. Additionally, we found that the gesture-based system exhibited significantly more sense of agency when the input action is accompanied by haptic feedback compared with visual feedback.
So these works are just scratching the surface in terms of what we can do to enhance agency, bonding, attachment, and so on. So the social components of touch, I think, is very important, and it would be great to do more work in this space, right? So I want to talk not just about haptics, but also about other sensory devices that we've done in our group. And we always say we try to create magical experiences in some sense. So we combine my own background in signal processing and physics with computer graphics and design thinking to some extent. So I put the slide up in many places and I say, we try to do magical experiences, and the best way to do magical experiences is, levitation. Right? So this is something that we've been working a lot in our group, and we've taken this from Professor Friedrich. So this is a video from my colleague Diego, where he shows.
Entonces, con un poquito de concepto mágico, si vamos Virgarnium leviosa. A ver, hemos destrozado un poquito la sorpresa. Bueno, pues ahí lo que tenemos es una partícula nada más, ¿vale? Y como podéis ver, sigue los movimientos de la varita, ¿vale? Entonces, lo bueno, la podemos mover como queramos en el espacio, ¿vale? Pero lo que es muy chulo es que si la mueves muy deprisa, puedes hacer eso.
Puedes hacer formas.
Aquí ahora mismo...
Una mariposa.
Sí, lo que seguimos teniendo es solo una partícula. Lo que pasa es que se mueve tan deprisa que tu ojo, tu cerebro lo que ve es la forma que está revelando.
Qué bueno.
Después lo coloreamos y puedes generar ese tipo de formas que están ahí sin trampa ni cartón en el espacio. Es una telita de seda muy ligerita y unas partículas que usamos para levitarlo. Entonces, cuando lo colocamos ahí, a ver si...
Esto para que veáis que se pueden hacer levitar objetos todavía más grandes.
Fíjate, Carlos, que lleva sorpresa.
Y no solo eso...
¡Wow! Es alucinante,
¿Qué es eso, Carlos? ¿Qué pasaba ahí?
¡Qué guay! Es una tela ahí.
Ahora, quiero que veáis.
Se consigue proyectar imágenes sobre esta tela.
Sí.
¿Qué sonido?
So I'm sure there are a couple of people here who speak Spanish, and I don't know if you recognize the co-host there. He's a F1 driver, so that was the connection with the Formula 1 there. So we can do levitation, and the great thing for what we do there is it's the same hardware, right? So the same Visuo-Haptic device, I will talk. It's a single particle that's gravitating right now, right? So the way that works is quite straightforward. So we have two speakers, the top and the bottom, and it's the same speaker that we use for the Visuo-Haptic generation. And it's this node where the particle suspends itself. Right? So as long as the weight of the particle is less than the force that's exerted by the ultrasound waves, it will stay there. And then we can update the position of the particle by turning the speakers on and off in different arrangements. So what we have here is 16 transducers. So you can see like 4x4 top and bottom arrangement. And if there's a particle here in the red dot, we can move it from here to this central location, so over here, by turning these two on, turning them on, and keep the rest of them off. So we go from this pattern to this pattern, the particle shifts. That's how we move the particle. That's quite a simple movement, but already with this simple movement, we can do some nice things, right? So let me show you. We don't have to levitate just polystyrene beads. We can do other things. This is a coffee bead that we levitate. We put hot water there, and I guess some people can call that coffee. If you like your coffee with milk, then you can levitate some milk there. So it's, if you want a snack to go with it, then there's a little bit of meat there, there's some lettuce and bread. That's a little mini burger. So we can levitate a lot of different materials. There's no limitation there. And the way levitation works is, so we are pinching the particle. So it's like, you use a hand and you grab a small object with your hand. That's sort of what we're doing. Instead of your hand, it's the sound waves that's creating this levitation. So a particle is trapped by sound, and a trap is a point towards which forces converge in all directions. So all the forces are coming to it. And that's sufficient, right? So, I mean, if you have that, you're going to have levitation, but it's unstable by itself. So what you want to also have is that the pressure amplitude is minimum. So it's a minimum point there. You can translate this set of requirements into an objective function. So then you can do optimization. So the way you do that is, right, so you set up, you assume that the particle is a small sphere. So all forces are acting towards it in a point. So you can just add those forces up. And it's given by this objective function here. So I'm not going to go into the details of how we come to this. But we have the key thing here is we have three different weights: Wx, Wy, and Wz. Okay? And Wp, let's forget about that for now. So if we look at these three weights and we get these solutions, I'm not going to bore you with a lot of maths. Just hang in there, right? So there are three solutions here of what's called twin traps, vortex, and bottle. So that's how the amplitudes and phases look. But what's more interesting is if you look at the transducers, right? That means if I have 256 speakers, I'm going to turn them all on. What do those speakers look like? So what is the phase of those speakers? This is what I get, right? So I mean, this is some solutions we get for twin trap, for vortex, and bottle. We got the solution and we were like, well, I don't know what to do with that. That's nice, but basically what this says is that every time you want to move a particle to a new position or levitate a bead to a new position, you have to compute this solution, right? But actually, it's quite interesting because if you think of this as a focal point where you focus all the sound waves into one point, and then you do something to it, right? So if you do that, then if you take this focal point and you subtract this from this solution, you get these beautiful signatures, right? And what these signatures mean is that you don't need to do this optimization every time. You simply say, okay, I want a particle here. Tell me what the focal point is there, and apply the signature. Then you have levitation. So whatever you do for haptics, you can simply take the haptic solution, add the signature, and you will have levitation. So it's the same thing there. So that's the nice thing. So once we realize that, what we did is we took a visual stimuli, and we'll show you what we can do, right? So we can combine visuals with haptics and with audio signals. So let me first show the video and then explain to you what happens. So this is one polystyrene bead that's moving so fast that you don't see it.
3, 2, 1, 0.
So we time multiplex levitation with haptics, and the particles don't fall, so we can do them both simultaneously. And also we are using, even though we are using ultrasonic speakers, you can hear audible sound because we do amplitude modulation on them. So what I showed you there was single particle. Right? So if you want to have many particles, you want to levitate 30, 40 particles to create a large volumetric display, then you need to go to acoustic holography. So what we can do then is, if we have a pattern like this, we are given some amplitude pattern, and we're looking for amplitudes and phases of these transducers. So there's a very old algorithm from 1970s called Gershberg-Saxton algorithm. Simply use that, and basically what it says is, if you want to know amplitude and phase of the transducers, and you've given some amplitude somewhere, you arbitrarily assume some phase for it and go back and forth. Right? So you just iterate back and forth 20 times, 30 times, 100 times, or you can set some criteria. And once you do that, then you will get the solution. This is great, but it's quite slow. This is what the algorithm tells you to do. Where you start with some field, and then you drop things out and you come back. This is very slow because you need to do lots of calculations in an iterative step. And you cannot do that for POV content. Right? But what you can do is, if you say, I don't care about the fact that it's a phase-only array, we can do phase and amplitude modulation, then you can get rid of that term. And when you get rid of that term, so what happens is that you can move it. Oops, I went too fast. So you can move all of these calculations out the top, which is a computationally intensive step, but that step is outside of your loop. So once you do that, then it's very fast iterations. Once it's so fast, we can do a POV computations of 40,000 frames or larger number of frames per second updates in many particles. Wait, I missed this bit. So you can see here, what we have is we have actually 3 polystyrene beads that are being levitated, and we can have the different colors, and you can see it's all coming together there. And we can have it with haptics and with audio. Here is the same POV content with audio. Sorry. And all 3 now with audio, haptics, and levitation. So far, I've been showing you how we can levitate 1 particle at a time, maybe 2 particles, 3 particles. But can you lift the whole thing? So can we levitate large structures too? So that's something we looked at as well. I'm just going to show you how it works. What you see here is that the particles are stuck to some fabric, and now we lift the whole fabric with this particle. we can do more, right? So we don't have to just levitate one of them at a time. We can do more storytelling. So we have here fabric, strings, and we can integrate a physics engine with it, so it feels more realistic. The one thing you would have noticed, or I don't know if you noticed, is we show how we bring a lot of things together, but we never show you how we separate things out, because we don't know how to do that. So we can stick a lot of things together, but we can never stick them. But the other thing that we've been working on is combining these speakers and transducers with 3D printed structures, right? So the problem with the current arrangement we have with the speakers is they're all about 1 centimeter in diameter, the speakers, and we're talking about 40 kilohertz sound wave. So they are sampling we have from the transducers is not at microsampling rate. Right? So if you want to have them create very high fidelity sound fields, then they have to be about 4 millimeters diameter, so that you can have dense patterning. Right? So the way to overcome that is to put some 3D printed structures on top of it, and those structures then act like new sound sources, so we can have much better control of the sound field. So here is an example of what we did is we had some speaker arrays below, and we put these 3D printed structures, which we call like acoustic metamaterials, and then this transducer array can then shape the sound field to go around objects and obstacles, right? So you have an obstacle that in principle would block the sound field, but because you have this metamaterial on top of it, you can shape the sound field to go around it.
This is Soundbender, a project which marries acoustic metamaterials with phased array transducers. The metamaterial plate bends sound waves around solid objects. It takes the form of a flat metasurface which sits atop the phased array transducers and bends the sound waves in a tulip shape with a cavity at the center. This arrangement enables many forms of dynamic behavior based on the sound wave pattern being output by the phased array. In each case, the sound bending nature of the modulation is maintained and can be steered in one or another direction by staggering the phases of the transducers beneath the metamaterial. If this staggering is done in a convex pattern, then the sound bending shape can be elongated and stretched. The beam steering operation is shown here clearly as the sound waves are bent around the solid piece of dry ice and are visualized in the gas sublimating from it. Another use of this device is in the generation of mid-air haptic feedback on the far side of solid objects, represented here by blocks of Lego. Finally, acoustic levitation can be achieved around obstacles, as shown here by this polystyrene bead suspended above a Lego man. It can be steered to the left or to the right as before.
And the last piece of work we've done is trying to do all of this thing with just one side. So we have here, up to now, everything I've shown you, there's no interfering object in sound field. That means I cannot have structures like this in the field because that will destroy the field. But so what we've done now is we've combined full solvers with some high-speed approximations so that we can have such objects in the environment and still do this kind of levitation. Okay, so the nice thing about this last work is we can combine this with haptics in the environment. Right? So you can have physical objects that scatter the sound and you can still use that to create haptics and levitation. Levitation is easy to show, that's why we showed levitation. Yeah, so I think what I want, I mean, this whole talk is about showing that there's a world of possibilities in combining visual and auditory information using acoustic holography. So these are some examples of, I mean, this was already like 5-6 years ago when I thought that this is the best I could get with acoustic levitation, where you have maybe a dog that looks like a dog, feels like a dog, sounds like a dog, and you can hear it. Right? So it's going to, it can have this full immersion for you, right? And all you need is this little platform that's in the environment for you, and you suddenly have this device, this shape appearing in front of you with full perspective correct visuals, video, and haptics and audio with it. In principle, it's possible to make it edible as well, so it can be any material you want. So that's possible. Yeah, I really hope it's possible for us one day to have multi-sensory experiences which are much more than just functional experiences. I know I showed you two halves. The first half where we were trying a little bit to have something that's much more experiential, and the second half which is functional. And we show you how we can combine levitation with haptics to create multi-sensory devices. But the future really has to be much more social and engaging rather than functional. We don't want button clicks and buzzes. What we want is storytelling and narratives where the person feels emotionally attached to this experience. A lot of the work that I do nowadays is not me. I have a whole range of people helping me with this work. These are all some of the people who have been through our group or interacted with us. And I'm sure I've missed lots of other names of people who work with me. In fact, I think the way this thing happens is what Charlotte was saying before, that now if I go into my lab, people are scared because they think I will break something. So just Sri, yeah, good, I'll give you a demo, but don't touch anything. That's the way it's been. Yeah, so these are all the people who funded our research. I'm happy to take any questions.
Thank you very much. Time for questions. The first one was over there.
Excuse me. Hi.
Yeah.
I have a question. So I see this system that you have to have parallel arrays. Is it possible, or can you envision some sort of acoustic lens? You embed this technology in something that is not so non-ergonomic.
Yeah, sure. So I mean, it's true that a lot of things that I showed you were top and bottom arrangements. But actually, this video that I showed you here, I'm going to show it again. Here, and you can see it's only the top, bottom here, and the top is arbitrary; it can be anywhere. We need it. We need so many speakers. They don't need to be in the same plane. They can be, but I think that's going to come down to the design of the interaction context. How you hide them in it, right? So it could be hidden in some prop or in some other location, so you don't see it. But it's possible to hide them. The other challenge that I don't have a simple answer to is what is the working volume you can have. So this volume is about 10 centimeter cube, so it's 10 centimeter, 10 centimeter, 10 centimeter on each dimension. I don't have a simple answer on how to make it bigger. We can make it longer by adding more, but I cannot. I can go maybe 100 centimeters times 10 centimeter by 10 centimeter, but not 100 centimeter cube. Not yet, at least. I don't know if I'm answering what you asked.
There was a question here.
I have a question like, how did you take care of the reflected waves to transmitter, to actuators? Right? You always have this reflected wave.
So in the top and the bottom arrangement, there's a standing wave. And in fact, even here we have a standing wave. And what we're doing is a full boundary element computation, so modeling. So we we know what this object is in the environment, or we know how the sound is being scattered, and we take that into consideration in shaping the focal points. Once I know what the focal point is, then I apply the signature to the levitation.
Okay, please.
Well, piggyback on that, do you need a deflecting surface then, or can it go into free air?
We can do free air as well. We don't need and we actually I accidentally deleted the video probably, but I have in fact back in 2015 we demonstrated for the first time where we can have one side transducers and we grab an object that's far away and pull it in. I think for all the Star Wars and Star Trek fans, that's what is this? See, I don't remember the name from Star Wars, where they trap something and pull it towards them. Exactly, a tractor beam. Thank you. I'm such a crazy fan of them. I don't know the word. But the thing was, in 2015, that was the 150th year of the Star Trek franchise, and we had so many news media outlet wanting to talk to us because we showed a tractor beam, and I don't even watch them, so I don't really know what. I confuse Star Wars and Star Trek, which is terrible.
Actually, sorry, this is following my actual question was, well, how heavy of an object would you levitate? And then B, also kind of, were you using any kind of, I saw the OptiTrack cameras, using any kind of feedback loop with that, or is that vector mapping to know where the surfaces are?
So the first question is the weight of the object. So it's more useful to think of density rather than weight, because as you can see here, we have 4 polystyrene beads that we are levitating, but the fabric is quite light. So the density that we can levitate is 1 gram per cc. About. We've done 3 or 4 grams per cc as well. So we've done like zircon crystal, which is like artificial diamond. But we cannot. We can only levitate a few of them at a time. So we cannot levitate 5 kilograms. That's our weight. And the second thing about the OptiTrack and the tracking is mostly for a feedback loop on lifting these objects. Right? So we want to know where they are in space. You can also do open loop where you just assume it's there.
So how much is it much better when you have to close loop feedback? Or
the closed loop versus open loop is about the interaction context, not about the levitation working or not working. So it doesn't really affect that.
I mean, this is so cool. When you look at it, it's like, but I also know that every time I test the ultrasound displays, very subtle.
Yeah.
So what is the, so I'm assuming that there are some data or whatever. So obviously, I really put it where it's best, but what is it that limits the strength?
So it's never going to be as strong as Vibrotactile sensation. So I think that's not going to be. It's not a fair comparison in terms of amplitude of the signal you get. But it can be. So the ultra lead device that you see, there might be some capping happening in the maximum amplitude because it's crazy that different regions have different guidelines for safe ultrasound use, which has nothing to do with the way we use ultrasound. It's about like diggers and the air traffic control there. So that's where the safety guidelines for ultrasound use have come from. But just because it's a commercial entity, they just decided, okay, we will. That's what it is. That's what it is. We will follow it, even though it's for your hand. Apart from that, I think the sensations are, people can definitely feel the sensation and they can feel differences in the different types of the sensation. So it's not that they miss specific subtle details, but I take your point that when you experience that and then you experience the Vibrotactile, then you say, oh, that's much stronger. So there are different things though. Yeah, I feel like. Yeah.
I was just curious because you could find that, I'm guessing, but what happens is you put the hand.
No.
That actually don't.
No, I mean it's it's not possible. At 40 kilohertz, the sound is going to just bounce off your hand. So it's not going into your body at all. Yeah. So there's no danger of anything like that. But we cannot increase it. It's physically not possible to increase it to the extent that you are going to feel this strength that's competing with Vibrotactile. It's just on the one.
Exactly. I'm thinking wind, for example. It's really, really windy. You have wind strong enough for your body or not.
Yeah, but that's different frequency, and
it's not that
you cannot be. Yeah, but you cannot focus it. So you cannot have both, right? So you cannot have that amplitude and focus at a specific point in your hand. So you can you have that strength, and then it pokes a hole right through your hand. That's not going to be possible. Yeah. Yeah.
Question here. Yeah, I was wondering about the holograms. If I understood this correctly, in your work you use light beads that are levitated. So the light source, the physical light source that is going through space. While I think holograms that I use, for example, as music editors these days, or this hologram too, that's not the
yeah, so
sorry, just a question would be, what would be the advantage of having a physical light source, like a physical bead, rather than just an optical illusion?
It's not a physical light source. I'm not sure what you meant by that. It's just a polystyrene bead, and the light source is somewhere in the corner over there. That's illuminating this polystyrene bead, right?
Yes, but I mean, there's a physical thing.
A physical object, yes. So
reflecting the light.
The word hologram is used and abused a lot and it means many different things are called holograms. So I would need to say exactly which type of hologram we're talking about. However, one thing that people, even in news media and so on, they say, oh, here's a hologram of someone coming. That's just a 2D representation of someone. So it's not perspective correct for multiple people at the same time, right? So in this holographic system, there can be 20 people standing around the particle, and they will all have perspectively correct views. And there's no fatigue and autostereoscopic effects. Yeah.
So would be the advantage that you would walk around the
hologram? Yeah. Yes. It would look as you would hope it should look. Yeah, and so collaboration should be easy. You can have two people standing and looking at it, and they will know exactly what they're talking about.
More questions? Yes.
So question. You said that for the BEM solver very similar to solver, but so you said also you have a GPU implementation for this. But do you have any thoughts? Because I guess for the GPU implementation also you need a big part and so on. Have you thought about doing embedded, like some embedded version of this system?
There are many questions there actually. So we use a BEM solver, but we separate it out a little bit because our mesh is static, right? So we can pre-compute a lot of things. So we are not doing BEM on the GPU in real time. We pre-compute the BEM and then we compute a transfer matrix. And then that transfer matrix we apply to compute the focal point in GPU real time. The second question, can I put BEM in the hardware? So what you were asking?
Like a Raspberry Pi controlling all the array.
Yeah, I don't know.
Because but if you pre-compute it, then it makes no sense. Yeah. If you compute on the fly, I guess.
Yeah. I mean, so in one of the earlier projects, we so here when we did this with a single particle levitating, that was in the FPGA. So we did the program. It's quite simple implementation, but it was done on the FPGA. That's why we could go 40,000 updates per second. Actually, the computation can be even faster than 40,000, but we're talking about 40 kilohertz sound wave, so there's no point in computing faster than pulse sound. How many sound waves?
I have a question. Did you try your devices in zero gravity?
Well, it needs sound, so if
No. You mean zero gravity?
No, we haven't tried that.
Because I wonder how much gravity, changing gravity in gravitational field will change
we can
performance.
In the zero G environment, yeah. So if we know what is the what kind of forces are acting, then we just need to put that in here, right? So,
will that mean that you can handle larger objects? They can move faster, more dynamic, maybe.
Yeah, I don't know. I need to think about it.
International Space Station. Get a European Space Station.
Yeah, interesting. Yeah.
Okay, and probably the last question before we go to a coffee break.
All the applications you have. Probably, any development on wearable, is there any opportunity to have those kind of technologies available for basement or kind of wearable application?
Yeah, it's a good question. So, I mean, at the moment, we've been focused on demonstrating the possibilities rather than seeing if we can miniaturize the devices and so on. There are two aspects to consider there. One is the physical hardware needs to be miniaturized. There are now transducers, surface mount transducers, so you could think of doing something like that. Then there's a power requirements. I mean, I never talked about that here. For haptics, actually, there's quite a lot. The device does consume enough power that you cannot put it on a mobile phone. But maybe there are ways to think about the holography computation where we try to specifically minimize transitions in the transducer. So we reduce the number of transducers that way and so on. That's possible, but it's not something we've looked at. Yeah, maybe. Oh yes, yeah. Yeah, true. Yeah, that's a good point. Yeah, we can certainly think of that.
Thank you very much. Very interesting. Thank you for many questions as well. A quick break before the last session of the day and before the evening reception. So you can have coffee outside if you wish to.
Claire Richards. I'll be talking to you today about my article that I co-wrote with Nicolas Misdaris and Roland Cahen, entitled The Reciprocity of Speculative and Product Design in an Industrial Framework. This research is part of a PhD industrial contract sponsored by Electronica. And I'm also affiliated with IRCAM and the Center for Design Research, two laboratories based in Paris. So in this project, our ultimate research objective is to push the possibilities for including more of the body in the listening experience. And to take this objective forward, we've structured our project around three main axes of development, which are the exploration of sensory capacities through experiments about perceptual thresholds and some more subjective judgments about one's own perception and preferences, the design and development of wearable audio-tactile devices, and the creation of audio-tactile sensory effects that are composed specifically for use with the wearable devices. And in this article, I focus mainly on the processes that are behind the design and development of those wearable tactile devices. So more specifically in this article, I wanted to delve into these processes behind the creation of these two devices created during my PhD research, which are the multimodal harness and RISM. So these two devices were both created in the context of the same research project, and they share certain similarities both in terms of functionality and inspiration. So they both aim to excite the sense of hearing through bone conduction and the sense of touch through vibrotactile simulation of the skin, and they were both designed with the same research objective in mind, which is, again, to include more of the body in the listening experience. However, they are obviously also very different. With this article, I wanted to explore the processes behind how each of these wearable devices came to be imagined and how the diversity of the environment surrounding the project has contributed to shaping both their purposes and forms. So in exploring the two design processes that are associated with each device, I gained more insight about not only each device's specific contributions to the overall research objective, but also about how the two devices' contrasting purposes actually ended up having a reciprocally beneficial effect, each feeding into the other's development. Throughout this presentation, I'll position the multimodal harness and rhythm inside the speculative and product design processes, respectively. So a few key terms will help me explain how I've chosen to organize the project in terms of these design processes, which are speculative design, product design, and also the design artifact. So speculative design, also known in some languages as design fiction, is a branch of design that doesn't necessarily serve what some may define as a practical purpose. Speculative designs can be somewhat removed from reality and its accompanying constraints, and aim instead to provoke thought more than generate capital. Product design is designed with a focus on reaching the market. The process is all about finding the best way for a future product to meet consumers' needs. It is necessarily rooted in reality and therefore confined by constraints like strict timelines and user acceptability. Finally, the design artifact is an output of the design process. It represents and manifests the design process and tells its story at any given stage in development. So a design artifact could be anything from a persona to a concrete object. In the case of this article, the two artifacts represent stages in development of two wearable audio-tactile devices. Essentially, they're prototypes. I'll quickly give some background about the auditory and tactile perception that they support. So in my research, I've focused on the perception of sound via extratympanic conduction, meaning sound perception that doesn't involve air-conducted sound waves that hit the eardrum. It can also be referred to as bone conduction, but that would be to exclude the evidence that other body parts such as fluids, muscles, and ligaments also contribute to this solid conduction-based perception of sound. Instead of focusing on extratympanic conduction via the skull, I have chosen to focus on the body in order to explore what characteristics of sound enable perception. Its position on the body, its amplitude, and its frequency all affect how well one may perceive the sound. Since contact-based vibrations are used to elicit extratympanic conduction, an interesting aspect to explore is the vibrotactile perception of the vibration, which occurs on top of the auditory perception of vibration in a specific zone of perceptual overlap. So here's a snapshot of that zone of overlap between auditory and tactile perception. Very simplified. Between 20 and 1,000 hertz approximately, it is possible to both hear and feel a vibratory signal that is displayed to the body. This research project is funded by a company specialized in haptics integration, Actuated. Sometimes it can be seen as a faux pas to mention outright where research projects funding comes from. But in this article, I address this fact directly because the project's financial partner has had naturally a direct impact on the design research process. So Actuated is a French startup initially specialized solely in haptics integration in clients' products, but now also specialized in their own product development. So the research project was initiated during the company's transition towards product development and has therefore been adapted over time in order to fit into the company's evolving business model. So in this sense, exploring the processes behind this design research has not only led us to consider how they have enabled us to produce new experimental methodologies and artistic applications of our research. It has also been about unpacking the impact that the commercial environment has had on our research. One way to explore these interactions between the purely research and purely commercial aspects of this project is by taking a deeper look at the design artifacts. So through the analysis, I'll try to show that the relationship between these seemingly dichomatic aspects of speculative and product design is actually not so black and white. In other words, something that has artistic value does not necessarily lose commercial viability, and vice versa. And I'll go into detail about the specific ways that the industrial environment or the product design process has impacted our research or the speculative design process in the next slides. With regards to the speculative design artifact, the multimodal harness was essentially designed with the motivation to challenge the status quo of listening experiences. Instead of using the ears, the speculative artifact uses the surface and interior of the torso to display audio-tactile effects via extratympanic sound conduction and vibrotactile stimulation of the surface of the skin. Our hopes for the device's functionality led us to create a tight-fitting wearable device, which includes 9 vibrating modules encased in hard plastic, which are suspended in frames across the spine, the ribs, and the clavicles. The frames around these modules allow the central parts to adapt their pressure at each of the different sites of stimulation on the body. Before users experience the multimodal harness, they first put on earplugs and noise-canceling headphones. So they become deaf, essentially, before they can experience the sound. And instead of just listening at one central point, which is the head, the user feels vibrations all across the surface of the torso, which are aligned with their auditory perception. The harness, therefore, may represent one way to blur the boundary of auditory experiences, arguing that the body itself can hear, not just the ears. RISM was designed with the intention of commercializing an accessible aspect of the research project in order to bridge the gap between our scientific exploration and a practical application of our work for our partner company. We chose to target the 3 points of vibratory stimulation that our initial studies showed as being the most sensitive to extratympanic sound perception compared to other points on the body, the clavicles and upper spine. Vibrations on either clavicle in terms of tactile effects could provide stereo-like effects, and the third position behind the neck offers more possibilities for front-to-back spatialized sensations. Another argument to limit the number and positions of the points of stimulation on the RISM device comes from cues from other body-worn listening devices, such as the neck-worn speakers now developed by acoustic companies like Bose and Sony. To explain how the two artifacts' development has proven to be mutually beneficial despite their contrasting motivators, I'll outline a few main positive project impacts. First, in both the speculative and product design processes, the artifacts have both directly contributed to our research objective. The multimodal harness has forced the user to reconsider their assumptions about sound perception and helps to imagine another evolutionary path of personal listening devices. Its functionality suggests that there could even be a future for inclusive listening devices adaptable to any hearing ability or inability, and perhaps even a future for body-based audio-tactile music composition. RISM presents a more comfortable, acceptable product aimed for audio-tactile listening experiences, which could represent an intermediary step in between the now and the possible future where the multimodal harness may exist as an acceptable consumer product. This figure exposes the ties between the development of the multimodal harness and the development of RISM. In our project, the speculative design process directly influenced the product design process. The multimodal harness served as a point of reference for the development of its commercial counterpart, RISM. We first took the time to analyze the multimodal harness and understand all of the aspects about it that would make it impractical for commercialization. Its highly complex construction, its uncomfortable fit, and its lengthy time of development, to name a few. These impractical aspects are more or less acceptable for its experimental use cases, but for a consumer product, they wouldn't pass. So we took each of these impractical aspects and flipped them on their heads to become a descriptor of an ideal consumer product. For example, where the multimodal harness aims to challenge the user's assumptions, a consumer product like RISM would need to serve the user's needs. While the multimodal harness can subsist as a prototype, a singular unit serving as a demonstration or experimental use, RISM would need to be produced at a mass scale. This analysis helped us to constrain the brainstorming process for the development of RISM, helping us to create what can be called the problem space. This is a term sometimes used to describe the working space that englobes a product's development, confined by temporal, ergonomic, regulatory, and material limitations. In other words, anchored in reality. The purpose of RISM is different from the purpose of the multimodal harness, but it still stems from the same project that created the multimodal harness and therefore upholds the same research objective, to push the possibilities for including more of the body in the listening experience. Beyond advancing our main research objective, the interactions between the speculative and product design processes also had social influences. They created a more productive dynamic and increased mutual understanding on the commercial and scientific sides of the research project. The 19-month timeline on this slide shows how the two design processes overlapped. There were phases of brainstorming, sketching, and prototyping all occurring in parallel on both ends of the speculative and product processes. Since we developed the two devices at the same time, we also developed mutual understanding. Colleagues at Electronica were able to better understand our experimental research objectives, and the research partners were able to better understand Actuanica's objectives because each began to directly participate in the project. This helped to integrate the project within the company and ease communication between the industrial and scientific project partners. In conclusion, the reciprocity of the two processes of design can be demonstrated through their interdependencies. The industrial environment makes it possible to pursue speculative design in the first place. And the speculative design process inspired the idea for the product design, which in turn fulfills the ultimate need of the industrial environment. So this type of approach may help to potentially prevent the products of a research project from simply ending up in a closet mid-development. It's not necessarily advisable to have both commercial and scientific sides of a project constantly interacting, but encouraging peaceful coexistence and mutual understanding between the project partners by actively exploring how a seemingly abstract research project can be brought back down to earth through a connection to real-world users can end up advancing everyone's objectives in the long run. As a next step to follow up on this research, we will take a look at other projects in audio-tactile wearable technology in the search for commonalities in addressing this commercial research dynamic and explore the diversity of speculative methods in multidisciplinary design projects. So thank you so much for your attention. I'm sorry I couldn't be at the conference, but I would be very happy for people to reach out to me directly by email to discuss any of your questions or thoughts about this work. Thank you so much. Have a great conference.
Hello, can you hear me, see me? Yeah, okay, I can hear something. Okay. So let's close this. Okay, hello everyone. My name is Francesco Soave. I'm doing a PhD in Media Arts and Technology at Queen Mary University of London. And today I'm here to present designing audio feedback to enhance motion perception in virtual reality, which is a recent user study that we conducted in the last few months. And first of all, I'm sorry I'm not there, but thanks to the organizer for making it possible to have a mixed mode conference. So first of all, let me introduce a bit my research and what I've been working on in the last couple of years. So the keywords are, sorry, I heard something.
Yes, one sec, we didn't prepare the screen here.
Okay.
Are you sharing your screen?
I am sharing.
Share content. Ah. Sorry about that. Now you can. Now you can go.
Sorry?
Now you can go ahead.
Okay. So did you hear the introduction?
Could you maybe repeat again?
Okay. So, hi, my name is Francesco Soave. I'm a PhD student at Queen Mary University of London at the Media and Arts Technology Center for Doctorate Training. And today I'll present an experimental research that we conducted in the last few months. And the title is Designing Audio Feedback to Enhance Motion Perception in Virtual Reality. So first of all, I want to say I'm sorry not to be there in real life at the conference, but thanks to the organizer for making it possible to have a mixed mode conference. So first of all, let me introduce my research with a few keywords. My research focuses on multisensorial virtual reality. So we don't use just vision, but also sound and haptic feedback. And the focus of that is to study motion perception and how multisensorial environment can influence perceived motion or movement in VR. So here we have a couple of screenshots from previous research we conducted. We study motion perception in these visual settings, basically, where it's a first-person point of view of a person sitting on a train that is moving linearly. And to put it simple, we apply different types of stimuli like sound and haptic, vibrotactile, feedback specifically, to see how users change their experience of perceiving movement. Just a few words on motion, because there's a lot of research that focuses on different types of motion in VR. Action and self-motion, which is also called the illusion of motion usually. And it's the kind of sensation that you experience in real life when you look a train at the platform and the train starts moving and you feel a bit dizzy. And usually, I'm pretty sure you've experienced it sometimes. And in VR, usually it's one of the causes of motion sickness. But then there's a lot of other studies that also focus on psychophysical aspects like speed, are often multisensorial, so they often use sound or vibration or other types of stimuli, but they're also very, very different. And there are some of them that puts together very different things. So in our case, we use vibrotactile haptic feedback, and this over here is the type of sensor that we used. It's a low-felt L5. It's a voice coil actuator that vibrates. And we applied 8 of them on a chair, and you can see the position here. So we aim at producing a sort of full body vibration to the back and the legs of a user that is sitting on a chair, wearing the VR helmet and so on. The vibration when doing haptic studies usually can be designed as you define your own patterns of vibration by generating a signal and modifying frequency and amplitude. Or like in our case, we use the soundtrack of the virtual environment to actually drive the actuators. So it's pretty much the same signal that you hear through headphones. You also it is also sent to the actuators. So our very first study was about basically very exploratory and was about testing the setup that you can see here and understand the actual role of haptic feedback and sound on self-motion in VR. And I'm introducing this because the paper that the article that I'm presenting today is based on the results of this study. So this is just to give you an idea of how our setup looks like. So here's the chair with the VR and the amplifiers. The user is sitting on the chair, experiencing the animation. And in our first study, we decided to compare different experimental conditions with different stimuli, basically. So we found that yes, haptic and sound has positive influence on perceived self-motion in virtual reality, but we also found some when talking to the user after the study, we found that there were some inconsistencies between the different stimuli, and that's quite important in multisensorial settings because inconsistencies across different stimuli can actually break the illusion completely of the virtual environment. And in particular, some participants said that the sound was not very matching with the visual. For example, if you notice in this study, the user was in a tunnel, and some participants said, yeah, I was in a tunnel, but the sound sometimes seemed not suggesting that. Or another person said, oh, but I was first person sitting inside the train, but I thought the sound was more like I was outside of the train looking at the train. So these sort of things. So basically, that's where the research question of today's article comes from. How do we design and evaluate stimuli in multisensory VR to ensure that there is some cross-modal congruency in the scene? So basically, we designed another study, and that's a bit experimental, meaning that it's not easy to find literature that does this type of user study in virtual reality. So I took inspiration from other types of studies that are often done in sound design when comparing different types of sounds. Basically, I designed 4 audio samples, and this is the visual setting. The train will move forward, and I will show you the videos in a couple of moments. The train accelerates, and there are different levels of velocity of the train, 3 different levels, basically. So there's 12 different types of animations that the user can experience. And after reading some literature on comparing different types of sounds between them, I identified 3 properties that I was interested in: realism, matching, which is coherency, basically, and plausibility. So basically, the user had to watch a video, and then in VR, obviously, and then rate with 3 sliders how real it was, how plausible they think it was, and how well did the sound match with the animation, basically. And you can see here there is a spectrogram of 4 different sounds. Each sound was made of 2 samples. One of them, it's lower in frequency, and it's pretty linear, and it's representing the sort of engine of the train, while another one was changing in pitch because the train is accelerating in the animation. So that was made on purpose to suggest acceleration. One of the sounds, sound number 3, is called an anchor sound, and it's bad. Like I purposely made it to be bad. So because when you do user studies where people had to use Likert scales, like in this case, all the sliders, they need to have sort of edges that they know. Otherwise, they might risk rating everything very high or very low. So this sound 3 was designed purposely to be very bad. And we had 22 participants who performed the study completely remote and unsupervised. And after they witnessed the 12 animations, they were asked to rank the 4 different sound, in which one they thought was the most suitable in the application, basically. And let me show you the video before I go to the results. Okay, so these were 4 out of the 12 possible sounds. that I picked just to show you the difference. So in terms of results, well, these are the box plot, and we can see the 4 different sounds on the horizontal axis, 1, 2, 3, and 4, and the 3 different speeds for each sound. And this is the ratings for realism, this is for plausibility, and this is for matching. And we can already see there's a trend in which sound number 3, which was the worst one, is always pretty much always the worst, rated lower, and that's expected. With this exception here, which I'm not sure why it's rated higher, because that's not expected, but it's still not as good as sound 1 and 2, which are instead rated pretty high in all 3 parameters. So a postdoc analysis confirmed the box plots, showing pretty much there's always a statistical difference between them, except for sound 1 and 2, which are not significant between them. And if we look again at the box plots, sound 1 and 2 are pretty much similar always. So meaning that people really didn't prefer one over the other. So at the very end, as I mentioned, the users were asked to rank the 4 sounds depending on which one they liked the most. And most people actually ranked sound 1 as the first one. So this, the result of this is what we used for the following study, which we carried out, and was again a study with Vibrotactile feedback to study perception of motion. And so aside from the quantitative results, I think with from the final quick interview that I did with the participants, there were some interesting thoughts that came out. And I think it's pretty interesting actually points. So first of all, the concept of realism, because I've asked people to rate the realism of the animation, but that might not be necessarily the case that you need a realist application. So I think a lot of times when we design, we assume we're looking for something that is real, but I don't think it's actually necessarily always like that. So perhaps that's an important point to consider when designing VR application that wants to or aim to simulate the real world, because obviously a lot of VR applications are done explicitly to simulate that, like flight simulators or training devices. But that's not always the case. So another interesting aspect was the user expectation. So in fact, if I ask some of you to think of the sound of a train, it's very unlikely that me and you are thinking the same sound, because probably we have a very different experience, a very different expectation of how a train sounds like, and in fact, that could influence quite a bit what your preferred animation could be, for example, or how your experience would be. And finally, another point is about background sounds. So, in fact, if you consider new trains, they don't really sound actually. When you're on it, they are pretty quiet. You don't hear the engine. But if you ask me again to think of a sound of a train, I know exactly what I'm thinking, and it's not completely quiet. So that's also another aspect, is that when you're usually traveling on a train, you don't focus much on the sound of the train. So that goes along with the user expectation and the realism to give a much broader implication on the user experience. So, yeah, thank you.
So we'll start with questions. Perhaps I could start with one. In your video, how much do you think the degree of realism in a visual scene would create differences in the degree of realism that is perceived auditorily?
Okay, I'm not hearing very well. Can I ask someone to type the question in the chat?
How about if I drop in this one?
Francesco, is it possible that your audio is very low?
My microphone?
No, the output, the speaker.
No, I hear you well now. Before I heard all crackling sound.
I'll repeat my question. So for thinking about cross-modal congruency, how much do you think the degree of realism in the visual presentation would affect the perceived realism of an auditory signal?
So you asked how much do I think the realism?
So in other words, as you start changing the realism of visual that you're presenting, how is that going to affect my perceived degree of realism of the concurrent auditory sounds?
So if I change, increase or decrease the realism, how it's going to influence the coherence?
Yeah. Yes.
So I think, in my experience, I think there's a sort of limit where you can increase realism up to a certain point. But I think I read the paper actually that too much realism actually might feel less realistic and so less plausible in VR. And I don't remember if that was a multisensory setup. But I think the point is, I think I should have framed that question differently, because I wasn't looking for, obviously my animation is not realistic. So perhaps the question of realism wasn't meant to be realism as in the real world, but more of realism in compared to, for example, your experience of being in a train. I don't know if that's answered.
Okay. Yeah, so any other questions? Because I'll just relay them down here. Okay, so there are no further questions, and thank you very much for your presentation.
Thank you. Thank you.
The final presentation for today is on using audio recordings to characterize a soft haptic joystick. And Ildar's going to do the presentation. Thank you.
Thank you very much. The material I'm going to present is part of the PhD studies of my student Joshua Brown. He's the first author of the paper and he did all experimental work. I was only supervising. And this is a preliminary result was the development of new type of soft haptic interfaces using particle jamming. Joshua is currently in Canada. He got an exchange grant. He's doing experiments at University of York in Toronto at the moment. So most of you probably know about particle jamming. So if we have multiple particles in a sealed environment, we can control stiffness by changing the pressure of this cavity. So if we create negative pressure vacuum, it becomes stiff, hard. If we release the cavity, if we add air inside, it will become soft. So we had an idea, why not to try to use this for haptics, but we, of course, we are not the first one. So there were people, not a lot, but there were people working on particle jamming based haptics. What we thought of is putting Vibrotactile actuators inside these particle cavities. So if we put an electrovibration motor, coil type actuator, inside these particle jamming cavities, we can then try to play with vibration and pressure to achieve probably new and interesting haptic stimulation effects. So in here you see a simple design of our first prototype, which was reported at Haptic Symposium 2020. So it's a sealed box with quinoa seeds, small 1 millimeter seeds inside, an Actronica actuator made by company Actronica, and a way to control pressure. So with a vacuum pressure controller. We looked into at that time we looked into characterization of the device. We had an accelerometer on top, and we played different frequencies. We combined different frequencies of coil type actuator with different pressure levels, and we looked into frequency responses. At that time, what we found is that we can modulate the range of frequencies we can play, and of course the magnitudes, by changing the pressure. So by having a same interface, we can actually change the way vibrations propagate in the cavity. Of course, it was the first prototype, and we wanted to look more into perception studies, find a good way to control the device with feedback, and maybe look into applications in virtual reality or telerobotics. But first we started with more control and characterization, but we changed the form factor of the device. So we looked into building a haptic joystick, but instead of a hard handle, we used a soft particle jamming structure with now two actuators inside. So we placed two coil type actuators, one on top of the other, in a handle. Handle was completely soft, and like in the previous interface, we could independently control two actuators and pressure of the device. So if we create vacuum, it squeezes, it becomes hard, like a plastic joystick or of a plastic handle of a conventional joystick. When we apply air, it grows. It actually behaves by behavior of this shape depends on the thickness and quality of material we use for the shape. So there are a lot of design aspects to consider when we design such interfaces. So we wanted to, again, to characterize the device before we use it. And this time, here is a video of a photo of built joystick with an actuator and how it is designed for assembly. So now to characterize the device, this time we decided not to use accelerometers, but we decided why not to try to use a microphone, because basically what microphone will pick is vibrations, acoustic vibrations coming from the particles. And because particles, multiple of them, they will have complex physical behavior, we thought that acoustic information, which we can sample at high frequency, very often higher than accelerometers, we can capture this mechanics, this behavior through sound. That is why we decided to do a simple experiment. We attached a microphone on top of the joystick, and we played a constant frequency signal to the coil type actuator. It was a 15 Hertz acoustic wave. Then we introduced two conditions for pressure, pressurized and depressurized. And we also had two conditions when device is on its own and when device is in a human hand. So to understand whether there are any differences, whether we should consider propagation of acoustics and haptic waves differently for different situations. So here, time history of recorded sound. So it is about 250 milliseconds window. In blue and orange, you see two conditions. Condition S is when we had our interface soft, so it was not pressurized. It was atmospheric pressure, and there was no grasping for the blue line, so device on its own. And orange when device was in a human hand, so in a human operator, let's say controlling a remote robot with a joystick. We can see that behaviorally we have a similar patterns, but magnitude of the signal of acoustic waves recorded by the microphone, they are smaller in all of the situations when we have a device in a human hand. So that is a major difference here. Then we looked into frequency response of the device for the same, actually for the conditions when the joystick was pressure, now with negative pressure, so we introduced vacuum. And we looked into frequency response with and without human here. So overall, globally, we have similar response. However, if you look more specifically, we have different, probably resonant frequencies of the whole system are changing. When we have a device without grasp, it is lower than when the device is in the human hand. It is the first frequency, resonant frequency, is shifted towards to the right. It's all more than 10 to 100 hertz, so within the still within the range of the device built by Actronic. But what we learn from here is that by changing the pressure, we change we change the magnitude, but we also can potentially control the frequencies which we pass or not pass. So it's kind of a filter. Now we looked again for different conditions. This is a time history one of the signals when device was under negative pressure, with and without human. Similar behavior we had. We have observed reduced magnitudes for the cases when a human was grasping the joystick. And I will skip this because basically it's again similar results. Now we learn from here that overall stiffness, when we increase the stiffness of the device, so when we introduce negative pressure, device becomes like behaves like a rigid object. So frequency responses are more or less same. We can observe shifts in resonant frequencies, but still it is with more investigation, more data is required to look into this. Magnitudes are decreased for when the device is subject to negative pressure, which means that basically our actuator inside the particle jamming has less ability to move, because particles, the fluid becomes hot. And when the fluid is hot, the motor cannot move much, so its magnitude is restricted, magnitude of motion. That is why probably we see less acoustic power in the signal. And important conclusion that we do not really need to use accelerometers to measure vibrations. Very often for haptic devices, and it is also more practical to use microphones because we get higher sampling data. Now I will move on a bit what is happening now, because this was done about half a year ago. We have built a third prototype. Now it is a touchpad, still two actuators inside. A user can interact with a touchpad like with a touch screen, and we have two load cells. Actually, we have 4 load cells, which gives us an opportunity to measure normal pressure, as well as we can localize where we touch. And this device we are trying to use now to control a remotely operated underwater robot in Canada. So that is our collaboration with the University of York. So we have this underwater robot there, and the ideas we had is that our device, using particle jamming, vibration, and pressure control, can be useful to human operators to give information about robots' orientation, about robots' depth, and how close we are to the bottom of let's say, a lake. In this case, it is a testing swimming pool. Because the human operator has restricted information from cameras only. So Joshua is conducting studies, as well as another important aspect is waves. When a robot is subject to external forces, like underwater waves, our particle jamming with vibration, because we have two actuators, we can also transmit vibrations into one or the other direction. So user studies are now undergoing. Hopefully we'll have more results to present at the next Haptics conference or Robotics conference. And yeah, and one more thing we are considering is to replace hard handles for haptic interfaces with something soft and shape changing, because our particle jamming interface, in addition to vibration propagation and hardness softness, can also change shape. As you remember, in the first for the haptic joystick, it can grow not only up and down but laterally as well. So the shape can change with if we design the interface in such a way. So we would like to see if changing handles of haptic interfaces will change perception. For example, we will, in order to represent a virtual wall with a higher stiffness, we do not need to have a stronger motor, but we will simply have a handle which will become soft or hard depending on the current state of interaction with the virtual wall. Our hypothesis, we will need to test it experimentally in a few user studies, is that once we approach the haptic wall, if the handle gets more rigid, harder, with the help of our particle jamming, we will be able to see that users perceive a higher stiffnesses, while we do not change the actual feedback on the motor side. I think that's all, and I probably finished early. So Joshua did all technical work, and here are both of our emails. If you would like to, he has a website now. Okay, I didn't know. And the websites, so you can mail us if you have any more questions. Yeah. Thank you very much.
Questions?
It's okay if we skip as well.
No, I was going to ask one. So when you talked about the various variables that you wanted to reflect from the robot back to the haptic display, you talked about characterizing it as a hard and soft. Is there any intermediary states? And then in terms of the actuators within the display, what variables of control would you use to reflect depth, proximity, waves, etc.?
So there are limitations in terms of how we control pressure, because pneumatic devices like pumps, they even they have feedback loop, it is much slower than the Vibrotactile feedback loop, for example. So if we want to have intermediate states between vacuum and maybe atmospheric pressure, it will, the settling time for the device may take up to half a second. Because of this, feedback and human user, our perceptual system is much faster. So that may not be very natural for the device. So at the moment we are testing on-off, pressurized, unpressurized, basically. But if we manage to have a nice pressure control, which will be able to maintain intermediate pressure levels and do it fast, then we can maybe explore more different types of hardness and softness levels. But you are completely right. I claim a lot because that is what we want to achieve. But at the moment, we have technological limitations. Another issue I mentioned sound, because compressors, they are noisy, yes. So we have to put compressors to pressurize away. And the length of the pipe introduces latency and slow dynamic response. So there are issues when we deal with pneumatic actuation.
Thank you. Any other questions? If not, I'd like this one. Sorry. Yes.
Can you hear me?
Yes.
Okay. You said that your findings show that when you
put air into the joystick, the amplitude of the vibrations change, but not the frequency.
Yes, correct. Yes, our finding shows that majority of, we can easily modify magnitude. To modify frequency, we need to look more into control and measurements.
Okay, so is the change on frequency is desirable for your applications?
In general, yes, because it will be a tool. It's basically a filter which you can naturally have in your system design. Because frequency and magnitude will be coupled. It's a single body which behaves with mass, damping, inertia. So we ideally want to decouple frequency from magnitude. That is why coil type actuators are good for that. We use them. We don't use eccentric motor or vibrators. Yeah. So we want to control independently. Yeah.
Have you tried probably changing the size of these elements, these little elements in the joystick? Does that make any? So it influences the changes in frequency or not?
Ideally, the smaller they are, the better, because in that case you can have a uniform distribution of vibrations. But if you go to extreme level, like you put it in a liquid, complete liquid, that is like molecular level particles, then you lose particle jamming effect. So there is it's quite a complex physics. There are a lot of physics and mathematical modeling papers on that particle jamming effect. So the big particles don't make sense because they are macro objects which simply transmit. But small particles, one we found 1 millimeter was working well. We didn't really try different sizes. What is important is that particles themselves should be rigid. Because if they are soft, then it's probably a damping effect mainly, no transmission. Thank you.
Any more questions? Okay, I'd like to thank the speaker and all the speakers.